Hello, friend. Thank you for being here tonight. Some nights the world feels wider than it should. Stars breathe slower. Time folds in silence. Maybe that's just the mind listening to itself. Or maybe it's the universe whispering something we've spent centuries trying to hear. Tonight we're going to drift into a question that has lived in human hearts since the first person looked up, "Are we alone?" But we're not going to answer it the way you might expect. We're going to follow the light-infrared light into places our eyes could never reach. Places where alien solar systems are being born dying and hiding in plain sight. We're going to talk about something called 3IATLAS, a map, a portrait of the invisible, a tool that lets us see what we've been standing next to all along. Before we begin, if you find comfort in these quiet journeys, you might like to stay a while. You can gently tap the like button, subscribe, if you'd like more stories, told softly, and ring the little bell not for noise, but so the next quiet night can find you again. Now, let's drift. Imagine standing in a field on a moonless night. The stars above you, thousands of them, are scattered like dust across black velvet. Some are bright, some flicker, some have already died, but their light is still traveling toward you, crossing years, crossing lifetimes. You look up and you wonder, is anyone else out there looking back? It's a simple question. But the universe doesn't deal in simple answers. For most of human history, we couldn't even see most of the universe. Not because it wasn't there, but because we were looking with the wrong kind of eyes. Visible light. The light we see with our eyes, the light that paints sunsets and rainbows, is just a thin slice of reality. It's like trying to hear a symphony, but only being able to hear the violins. You'd miss the cellos, the drums, the bass that holds everything together. The universe is full of things that don't shine in visible light. Dust clouds, cool stars, planets forming in the shadows of their suns, all of it hidden, silent, waiting. Until we learned to see differently. Let's go back to the year 1800. A man named William Herschel, a musician turned astronomer, was experimenting with sunlight. He passed it through a prism, splitting white light into a rainbow of colors. Then he measured the temperature of each color using thermometers. Red light was warmer than blue. That made sense. But then he placed a thermometer just beyond the red in a region where there was no visible light at all, and it heated up. There was light there, invisible light. Light our eyes couldn't see, but our skin could feel. He called it infrared, beyond red. Light that exists in the spaces we thought were empty. It was the first time humanity realized we've been blind to most of the universe. Infrared light travels through dust. It passes through clouds of gas that would block visible light completely. It reveals heat motion chemistry. It shows us the birth of stars, the glow of planets, the whisper of molecules floating in alien atmospheres. It's not just another way of seeing, it's the way the universe has been asking to be seen all along. Fast forward to today. We have telescopes that see in infrared. The James Webb Space Telescope, launched in 2021, peers deeper into space than anything before it. It sees galaxies forming in the first moments after the Big Bang. It sees exoplanets, worlds orbiting distant stars, glowing faintly in the dark. But even Webb can't see everything at once. Space is vast, infinite maybe. To truly understand what's out there, you need more than one telescope. You need a map. That's where 3IATLAS comes in. The third installment of the Infrared Atlas. A collaboration of telescopes' data and decades of patient observation. It's not a single image, it's a mosaic. A portrait built from millions of infrared snapshots stitched together to reveal the architecture of distant solar systems. It doesn't just show us where planets are, it shows us where they're forming, where they've died, where the dust left behind is still circling like ghosts of worlds that never quite made it. 3. The Atlas is teaching us something profound. Alien solar systems don't look like ours, not even close. Some are chaotic, some are elegant, some are broken. And every single one has a story. Here's what most people get wrong. They think if we can't see something, it doesn't exist. But the truth is the opposite. Most of what exists, we can't see. Not because it's not there, but because it's hidden behind curtains of dust, veils of distance, layers of time. Visible light is blocked by dust, but infrared passes right through like a whisper moving through a crowded room. It reaches the places light can't go, the nurseries where stars are born, the graveyards where they die. Before infrared astronomy, we thought star-forming regions were dark, empty voids. Then we looked with infrared eyes and suddenly they were blazing, glowing with heat, packed with baby stars, embryos of solar systems, the universe in the act of creation. We weren't seeing new things. We were finally seeing what had always been there. 3IATLAS does this on a scale never attempted before. It maps not just one star-forming region, but hundreds. Not just one exoplanet system, but thousands. It shows us patterns, trends, the rules the universe follows when it builds solar systems. And the first rule, it's teaching us, there are no rules, or at least none that we expected. Our solar system, the sun, 8 planets, a neat arrangement from rocky worlds close in to gas giants farther out. We used to think that was the standard, the template. That's how solar systems form, we told ourselves. Orderly, predictable, stable. Then we started finding exoplanets. And everything we thought we knew started to unravel. We found planets the size of Jupiter orbiting closer to their stars than Mercury is to our sun. We found planets made of diamond planets, where it rains glass sideways planets with 2 suns. Planets with no sun at all. We found worlds that shouldn't exist according to our models, and yet, there they were, spinning silently in the dark. 3IATLAS shows us why. Because it doesn't just detect planets, it detects the environments where planets form, the disks of gas and dust that swirl around young stars, the places where gravity pulls matter together, grain by grain, until a world is born. And those disks, they're messy. Beautiful, but messy. Rings and gaps and spirals, clumps and shadows. Every irregularity is a clue, a fingerprint of something happening. A planet carving a path, a collision, a migration. It's like watching a crime scene slowly reveal itself. You don't see the event, you see the aftermath, and you have to work backward, piecing together what must have happened. That's what 3IATLAS gives us. Not answers, clues. Let me ask you something. Have you ever felt like you were missing something obvious, like you were looking right at it but couldn't see it? That's what humanity has been doing for thousands of years. Looking up at the stars asking, are we alone? But missing the answer because we couldn't see the full picture. Now, slowly, carefully, we're starting to see. 3IATLAS doesn't tell us there's life out there. It doesn't show us alien cities or radio signals, but it shows us something just as profound, the raw materials for life. The chemistry, the conditions, the time. It shows us water vapor in the atmospheres of distant planets, carbon molecules, methane, the same building blocks that gave rise to life here on Earth, floating in the skies of worlds hundreds of light years away. Does that mean there's life there? Not necessarily, but it means the universe is full of possibilities, full of places where the right ingredients exist, where the dice have been rolled. Whether they came up lucky, that's what we're still trying to find out. Here's the thing about space. It doesn't care about our timelines. Stars take millions of years to form. Planets take hundreds of millions. Life, if it emerges, takes billions. We've been looking for alien civilizations for less than a century. We've been able to detect exoplanets for less than 30 years. We've had infrared space telescopes for a few decades. In cosmic terms, we just opened our eyes. And already we're seeing things that rewrite the textbooks. Already 3IATLAS is revealing structures, patterns, oddities that challenge everything we thought we understood. Imagine what we'll know in another 100 years, another 1,000. Or imagine this. What if somewhere out there another species is doing the same thing? Looking up. Building telescopes. Mapping the infrared sky. Trying to understand if they're alone. What if their 3IATLAS is pointing at us right now? What if they're seeing the faint glow of our sun, the warm signature of Earth, and wondering the same question? The silence between stars isn't really silence. It's full of light we couldn't see, full of stories we're only beginning to read. At 3IATLAS is teaching us to listen, not with our ears, but with instruments that catch whispers of heat, flickers of chemistry, the faint glow of worlds in formation. It's teaching us that the universe is not empty. It's crowded, chaotic, busy with the work of creation. And we're just starting to notice. You don't need to understand all of it. Not tonight. Just rest in the knowing that out there beyond the veil of visible light, beyond the dust and the distance, something is happening. Solar systems are being born. Planets are taking shape. And maybe somewhere in all that quiet chaos, something is looking back. So, tonight as you drift towards sleep, think about this. The light from distant stars takes years to reach us. The infrared glow that 3IATLAS detects might have started its journey before you were born, before your parents were born, before anyone you've ever known existed. And yet, it's here now, crossing the dark, finding us. We're not just looking into space, we're looking into time, into the past, into the future, into all the possibilities that exist between here and there. The universe is bigger than we thought, stranger than we imagined, and quieter too. But if you listen closely, if you look with the right kind of light, you'll find it's not silent at all. It's whispering, and we're finally learning the language. Now, let's move a little deeper. Let's follow that whisper backward in time to the moment when humanity first realized we'd been seeing only half the sky. Let's talk about the birth of infrared astronomy and how one invisible discovery changed everything we thought we knew about the cosmos. There's a kind of light you've felt but never seen. It warms your skin when you stand near a fire. It radiates from your body on cold nights. It's everywhere all the time, invisible and patient. For most of human history, we didn't know it existed. And because we didn't know, we missed half the universe. Let's go back to England 1800. William Herschel was already famous. He'd discovered Uranus 19 years earlier, the first planet found in recorded history that wasn't known to the ancients. He was a musician by training, an astronomer by passion, and a tinkerer by nature. One afternoon, he was conducting what seemed like a simple experiment. He wanted to know which color of light carried the most heat. He split sunlight through a prism, creating a rainbow on his table. Then he placed thermometers under each color, blue, green, yellow, orange, red, measuring, recording, scientific routine. But then he did something curious. He placed one more thermometer just beyond the red edge of the spectrum, in the empty space, the place where to his eyes there was no light at all. And it registered the highest temperature of all. Something was there, something invisible, something warm. He called it calorific rays. Later, the term infrared stuck, beyond red, past the edge of what human eyes could detect. It wasn't just a discovery of a new type of light. It was the realization that our senses had been lying to us. That visible light, the thing we trusted most to understand reality, was just a narrow band in a much wider spectrum. We'd been looking at the universe through a keyhole, and Herschel had just opened the door. But here's the thing. Knowing infrared light exists and actually using it to see the universe are two very different things. For over a century, infrared remained mostly a curiosity. Scientists could detect it in laboratories, measure it, study its properties, but they couldn't use it to look at stars. The problem was Earth's atmosphere. Our atmosphere is full of water vapor, carbon dioxide, methane, and all of those molecules absorb infrared light. They drink it up before it ever reaches the ground. So even though the universe was blazing in infrared radiating heat and hidden stories, we couldn't see any of it from down here. We were standing under a blanket trying to glimpse the stars. It wasn't until the mid-20th century when we started putting telescopes above the atmosphere on high-altitude balloons, on rockets eventually in space, that infrared astronomy truly began. And when it did, everything changed. The first infrared space telescope, IRAS, launched in 1983. It operated for only 10 months, but in that short time, it detected over 350,000 infrared sources. Most of them had never been seen before. Star-forming regions that looked dark and quiet in visible light suddenly blazed with activity. Galaxies hidden behind dust revealed themselves. Cool dwarf stars too faint to see with optical telescopes lit up like embers in the dark. It was like turning on the lights in a room you thought was empty and realizing it was full of people. IRAS showed us that the universe wasn't just bright and visible light. It was alive and infrared, pulsing, breathing, full of motion and heat and chemistry we'd been missing all along. And that was just the beginning. The Spitzer Space Telescope, launched in 2003, took it further. It could see cooler objects, fainter signals, deeper into dust clouds. It mapped the Milky Way in infrared, revealing the structure of our galaxy in ways optical telescopes never could. Then came Herschel, the European Space Agency's infrared observatory, which studied the coldest, darkest regions of space. Places where stars were just beginning to form, where planets were condensing out of primordial clouds. And now, the James Webb Space Telescope, the most powerful infrared instrument ever built. It can see the first galaxies that formed after the Big Bang. It can analyze the atmospheres of exoplanets. It can peer through dust clouds so thick that visible light can't penetrate even a fraction of the way. But even Webb, as powerful as it is, can't map everything. It focuses on specific targets, specific questions. To understand the broader picture, to see not just individual systems, but the patterns, the trends, the architecture of the universe, you need something more comprehensive. You need an atlas. That's where 3IATLAS comes in. The third installment of the Infrared Atlas. It's not a single telescope. It's a collaboration. A synthesis of data from multiple infrared surveys combined and refined over years of observation. It maps the infrared sky in unprecedented detail, focusing on regions where solar systems are forming, evolving, dying. Think of it as the difference between a single photograph and a time lapse. Webb gives us stunning snapshots. 3IATLAS gives us the motion, the context, the story. It shows us where protoplanetary disks are most common, which stars are surrounded by dusty debris, which systems have planets carving gaps in their disks, which ones are chaotic, turbulent still in the messy early stages of formation. And what it's revealing is this solar systems don't form the way we thought they did. Or rather, they do, but with so much variation, so much randomness that our neat models barely scratch the surface. Some disks are smooth and symmetrical. Others are warped, asymmetrical, riddled with gaps and clumps. Some stars are surrounded by multiple rings like a cosmic bullseye. Others have spiral arms like miniature galaxies. Every irregularity tells a story, and 3IATLAS is teaching us how to read them. Here's a mistake we made for decades. We assumed that what we couldn't see wasn't important. Before infrared astronomy, we looked at star-forming regions and saw darkness. We assumed they were quiet, empty, not much happening, just cold gas waiting to collapse. Then we looked with infrared eyes and realized they were the most active places in the galaxy, bursting with baby stars, glowing with heat, churning with the violence of creation. We thought comets were rare. Then infrared surveys showed us that almost every mature star has a debris disk, a ring of icy rubble left over from planet formation. Comets aren't rare. They're everywhere. We just couldn't see them. We thought planets formed in neat, orderly rows, like seeds planted in a garden. Then 3IATLAS showed us planets migrate, collide, get ejected into interstellar space. Solar systems are battlegrounds. Survivors tell the story. The rest are dust. Infrared didn't just add new data. It rewrote the narrative. Let me tell you about one system that changed everything. It's called HL Tauri. In visible light, HL Tauri looks like a faint young star surrounded by a faint glow. Nothing special, But in 2014, the ALMA telescope, which observes in millimeter and submillimeter wavelengths, cousins of infrared, captured an image of H.L. Tauri's protoplanetary disk. And it was breathtaking. The disk wasn't smooth. It had rings, multiple concentric rings, gaps carved into the dust like grooves on a record. Those gaps, they're the signature of planets. Young planets still forming massive enough to sweep their orbits clear of dust and gas. Each gap is a world under construction. H.L. Tauri is 450 light-years away. It's less than 1 million years old. In cosmic terms, it's an infant. And yet, it already has the architecture of a solar system. Planets are forming there right now, pulling themselves together out of the chaos. When astronomers saw that image, it was like watching an ultrasound of the early solar system, a glimpse of what our sun looked like 4.5 billion years ago, when Earth was just a clump of rock accreting in the dark. 3IATLAS builds on discoveries like this. It finds hundreds of systems like H.L. Tauri, each one slightly different. Some with more rings, some with fewer, some symmetric, some lopsided. And by comparing them, we start to see the patterns, the rules of formation, the conditions that lead to rocky planets, gas giants, or nothing at all. Here's something most people don't realize. Infrared light doesn't just show us where things are. It shows us what they're made of. Different molecules absorb and emit infrared light at different wavelengths. Water has a signature. Methane has a signature. Carbon dioxide, ammonia, silicates, each one leaves a fingerprint in the infrared spectrum. So, when 3IATLAS detects a protoplanetary disk, it's not just seeing a blob of light. It's reading the chemistry. It's telling us what elements are present in what quantities at what temperatures. It's like being able to taste a dish just by looking at it. You can tell if it's salty, sweet, sour, spicy, all from the light it emits. This is how we know that water is common in the universe. Not because we visited these places, but because we've seen water's infrared signature in the disks around young stars. We've detected it in the atmospheres of exoplanets. We've found it in comets, asteroids, moons. Water isn't rare. It's everywhere. And that means one of the key ingredients for life, at least as we know it, is woven into the fabric of planetary formation. Does that mean life is common? Not necessarily. Water is necessary, but not sufficient. You also need the right temperature, the right chemistry, the right amount of time, but it means the universe isn't hostile to life. It's full of the pieces. Whether those pieces come together, that's a different question. Think about what this means. For thousands of years, we looked up and saw only what our eyes could detect. We built elaborate mythologies around the stars we could see. We navigated by them. We measured time by them. We told stories about them. But we were only seeing a fraction of the picture. The brightest stars, sure, but not the coolest ones. Not the ones hidden behind dust. Not the ones too faint or too far to register on our retinas. Infrared opened a second set of eyes, and suddenly the universe doubled in size. No, it multiplied. Because for every visible star, there were dozens, hundreds of objects radiating in infrared. Brown dwarfs, protostars, dust clouds, debris disks. The sky we thought we knew was just the surface. Infrared let us dive beneath. And 3IATLAS is the map of that hidden ocean. There's a phrase in astronomy, extinction. It doesn't mean something died. It means light was absorbed, blocked, lost before it could reach us. Dust causes extinction. Thick clouds of it hanging between stars, swallowing visible light, like fog swallows headlights. In optical images, these regions look like voids, dark patches, empty. But in infrared, they glow, because the dust absorbs visible light, heats up, and re-radiates that energy as infrared. The thing that blocks us in one wavelength becomes visible in another. It's a reminder, absence isn't always emptiness. Sometimes what looks like nothing is just something we haven't learned to see yet. How many other things are we missing because we're looking with the wrong kind of light? How many answers are already in front of us, waiting for the right question? 3IATLAS isn't just showing us alien solar systems, it's showing us ourselves. Because every system it reveals, every disk it maps, every planet it hints at, it's a version of what our solar system once was. 4.5 billion years ago, the sun was surrounded by a disk, just like the ones we see in 3IATLAS. Dust and gas swirling, colliding, sticking together, grain by grain, pebble by pebble, boulder by boulder, until the planets took shape. Earth formed in that disk. So did Mars, Jupiter, Saturn. The moon formed from a collision in that disk. The asteroids are leftovers from that disk. We're made of disk material. You, me, everything on this planet, we're the remnants of that ancient swirl. When we look at HL Tauri, or the systems mapped by 3IATLAS, we're not just looking at distant objects, we're looking at our own origin story. Repeated, varied, played out in endless permutations across the galaxy. Every solar system is an echo of every other, different but connected by the same physics, the same chemistry, the same slow, patient pull of gravity. So, what happens next? Where does infrared astronomy go from here? There are plans for even more powerful instruments, telescopes that can see colder, fainter, more distant. Detectors sensitive enough to pick up the faint glow of Earth-like planets orbiting sun-like stars. 3IATLAS will continue to grow. More data, more systems, more patterns emerging from the noise. And eventually, maybe we'll have enough information to answer the question that started all of this. Are we alone? Not with certainty, perhaps, but with evidence, with clues, with a map of where to look and what to look for. Because that's what infrared gives us, not answers, directions, not proof, possibility, not certainty, hope. You've been lying here listening, and maybe you're wondering, why does any of this matter? Why spend billions of dollars, decades of time, all this effort, just to see what's hidden in the dark? Because understanding where we come from changes how we see where we are. Because every solar system we study teaches us something about our own. Because the universe is not a static painting. It's alive, evolving, creating, destroying, recycling itself endlessly. And we're part of that cycle. We're not separate from it. We're in it, made of it, connected to every distant star, every forming planet, every cloud of dust floating between galaxies. Infrared astronomy didn't just open new eyes, it opened new empathy. It showed us we're not unique, we're not special, but we're not alone either. Not in the sense of finding alien civilizations, not yet, but in the sense that the processes that made us are happening everywhere all the time. The universe is busy, and we're just beginning to see the full scope of its work. So, let the thought settle gently. Right now, somewhere hundreds of light years away, a young star is surrounded by a disk of dust. Grains are colliding, pebbles are forming. Maybe in a few million years, planets will coalesce. Maybe one of them will have water. Maybe a billion years after that, something will look up from that planet's surface and wonder if it's alone. And maybe it will build a telescope, learn to see in infrared, start mapping the sky, and maybe it will see us. A faint glow, a distant warmth, a system that's already old, already stable, already home to a species asking the same questions. We can't know, not yet, but we can look, we can map, we can follow the light that hides in the spaces we thought were dark. And that brings us to the next question. What exactly are we seeing in those disks? What are the rings, the gaps, the spirals? What stories are being written in dust and gas, and how do we read them? Let's drift a little closer to those hidden nurseries where planets take their first fragile steps into existence. Imagine a ring of light spinning in the dark, not a solid thing, but a cloud. Dust and gas, billions of tiny grains, each one orbiting a young star, colliding, sticking, growing. This is where planets are born, not suddenly, not violently, just slowly, patiently, grain by grain, over millions of years. And if you know how to look, if you can see the patterns in the chaos, the disk will tell you its secrets before the planets even finish forming. Protoplanetary disks. The name sounds technical distant, but really they're nurseries, cosmic cradles, the places where solar systems take their first breath. Every star begins its life surrounded by one of these disks. Our sun had one. So did every other star you've ever seen in the night sky. The disk is the leftover material from the star's formation, the scraps that didn't collapse into the star itself, but kept circling, waiting. Most of the mass is gas, hydrogen, helium, the same stuff that makes up stars. But mixed in are tiny particles, silicate grains, ice crystals, carbon dust, the raw ingredients of worlds. At first, the disk is smooth, featureless, just a flat plane of material heated by the young star at its center, cooling as you move outward. But then slowly things start to change. Grains bump into each other, some stick. Electrostatic forces van der Waals, forces tiny attractions that barely matter on Earth, but dominate in the near vacuum of space. A grain becomes a pebble becomes a boulder becomes a planetesimal. And once something grows large enough, it starts to pull on everything around it. Gravity takes over, the disk is no longer smooth, it's lumpy, clumpy, full of growing seeds that will one day be planets. Here's where 3IATLAS becomes essential. Because we can't watch a single disk for millions of years. We don't have the time, but we can look at thousands of disks, each one at a different stage of development, and piece together the story. It's like flipping through a photo album of strangers and realizing they're all aging. Baby pictures, childhood, adolescence, adulthood. You don't need to follow one person through time to understand the process. You just need enough snapshots. 3IATLAS gives us those snapshots, hundreds of them. Disks around stars that are 100,000 years old. Disks around stars that are 1 million years old. Disks around stars that are 10 million years old, already fading most of their material, locked into planets or blown away by stellar winds. And what we see is, these disks don't stay smooth for long. They develop structure, rings, gaps, spirals, asymmetries. Every irregularity is a clue, a signature, a planet's fingerprint written in dust. Let's talk about gaps. In 2014, when ALMA captured that stunning image of HL Tauri, the most striking feature wasn't the brightness of the disk, it was the gaps. Dark rings evenly spaced, carved into the dust, like grooves on a vinyl record. At first, astronomers weren't sure what they were seeing. Were these gaps real, or just artifacts of the observation? But the more they studied, the clearer it became. The gaps were real, and they were caused by planets. Here's how it works. Imagine a young planet still forming embedded in the disk. It's not solid yet. Not a rocky sphere like Earth or a gas giant like Jupiter. It's more like a dense clump, a gravitational knot pulling material toward itself. As it orbits the star, it sweeps up dust and gas in its path. Not all of it, it's not strong enough for that yet, but enough to create a noticeable dip, a cleared region, a gap. The bigger the planet, the wider the gap. The more massive, the sharper the edges. HL Tauri has at least 5 distinct gaps. That means at least 5 planets all forming at the same time, all carving their own orbits out of the surrounding material. And HL Tauri is less than 1 million years old. In cosmic terms, it's a newborn, and yet its solar system is already taking shape. But gaps aren't the only clues. There are also spirals. In some disks observed by 3IATLAS, the dust doesn't form clean rings. Instead, it curves sweeping outward in elegant arcs, like water swirling down a drain, or cream stirred into coffee. These spirals are caused by gravitational instabilities. When a disk is massive enough, dense enough, it can develop its own internal structure. Waves ripple through the gas. Density patterns emerge, and those patterns shepherd the dust into spirals. Sometimes a spiral is triggered by a planet. Its gravity disturbs the disk, and the disturbance propagates outward, creating a wave that persists long after the planet has moved on. Other times, spirals form spontaneously. The disk itself is unstable, fragmenting under its own weight. In rare cases, these fragments can collapse directly into planets or even brown dwarfs, objects too small to be stars but too large to be planets. Elias step by 2-27. A disk about 400 light-years away shows two prominent spiral arms. Scientists suggest these spirals are being driven by a massive planet, or possibly two embedded deep within the disk. We can't see the planets directly, not yet, but we can see the wake they leave behind, the ripples in the dust, the architecture they impose on their surroundings. Then there are the asymmetries, and this is where things get really interesting. Most disks aren't perfectly circular. They're lopsided, brighter on one side than the other, thicker in some regions, thinner in others. Why? Because disks aren't isolated. They interact with their environment. Nearby stars can pull on them, warping their shape. Binary companions, two stars orbiting each other, can truncate the disk, cutting it off at a certain radius. And planets, especially massive ones, can trap dust in specific locations. Imagine a planet orbiting through the disk. Its gravity creates a pressure bump, a region where dust particles slow down and pile up. Over time, that region grows brighter, more massive. It looks like a clump, a bright spot in an otherwise smooth disk. IRS 48. A star about 400 light-years away has one of the most dramatic asymmetries ever observed. Its disk has a bright arc on one side, shaped like a cashew nut. Scientists believe this arc is a dust trap, created by a massive planet carving through the disk. Inside that trap, dust grains are colliding, growing, potentially forming the seeds of additional planets. The disk isn't just a passive reservoir. It's dynamic, responsive, constantly reshaping itself in response to the objects forming within it. Now here's something most people don't realize: not all disks survive. Some are destroyed before planets can form. The young star at their center can be too active, too violent. It emits powerful stellar winds, blasting the disk away. Or it undergoes intense flares, heating the gas until it evaporates and escapes into space. Other disks are stripped by external forces. If a young star forms in a dense cluster surrounded by thousands of other stars, the intense radiation from massive nearby stars can photo-evaporate the disk. The outer regions are heated and blown away, leaving only a small, dense core. In these cases, planet formation is stunted. There's not enough material. Maybe a few rocky planets manage to coalesce close to the star, but there's no gas left to build giants, no reservoir to form ice worlds in the outer regions. Our solar system was lucky. The sun formed in a relatively sparse region far enough from massive stars that its disk survived intact. If the sun had been born in a denser cluster like the Orion Nebula, where thousands of stars are packed into a space just a few light years across, we might not be here. The disk would have been stripped, the planets wouldn't have formed, Earth wouldn't exist. It's a humbling thought. Our existence depends not just on the right chemistry, the right temperature, the right distance from the sun. It depends on where the sun was born, on chance, on cosmic geography. 3IATLAS shows us all of this. The disks that survived, the ones that didn't. The ones caught in the middle, still fighting to hold on to their material as stellar winds and radiation try to tear them apart. And by studying the differences, the variety, we start to understand what makes a solar system successful. What conditions lead to planetary formation? What conditions lead to failure? It's not just about having a disk, it's about having the right kind of disk, massive enough, dense enough, protected enough. For long enough, planets need time. Millions of years to grow from dust grains to planetesimals to full-fledged worlds. If the disk disperses too quickly, the process halts. You're left with a star surrounded by a faint haze of leftover dust, but no planets, no moons, no chance for life. timing matters. And 3IATLAS is teaching us how to read the clock. Let me tell you about TW Hydrae. It's one of the closest protoplanetary disks to Earth, only about 200 light-years away. It's been studied extensively because it's bright nearby and relatively old, about 10 million years. In optical light, TW Hydrae looks unremarkable, a faint star, a faint disk. But in infrared and millimeter wavelengths, it's a treasure trove. The disk has multiple gaps, at least 3, possibly more. Each one suggests a planet in the process of forming. The innermost gap is close to the star where rocky planets would be. The outer gaps are farther out where gas giants and ice worlds might emerge. But here's the twist. TW Hydrae is old for a protoplanetary disk. Most disks disperse within a few million years. TW Hydrae has held on for 10 million. Why scientists suggest it might be because the disk is more massive than average, or because the star is less active producing weaker winds, or because the disk is isolated far from disruptive influences. Whatever the reason, TW Hydrae is a survivor. And that's good news for planetary formation. The longer the disk lasts, the more time planets have to grow, the more time complex structures can develop. If TW Hydrae was closer, if we could visit it, we might see worlds already taking shape, atmospheres beginning to form, moons coalescing in orbit around young giants, a solar system in its infancy messy and unfinished, but unmistakably alive. Think about this: every planet in our solar system formed in a disk just like the ones we're studying. Mercury, Venus, Earth, Mars. They all condensed out of dust grains in the inner regions where temperatures were high enough to vaporize ice but cool enough for rock to solidify. Jupiter and Saturn formed farther out beyond the frost line, the distance from the sun where water ice could exist. They started as rocky cores just like the terrestrial planets, but they grew massive enough to capture hydrogen and helium from the surrounding gas. That's why they're giants. Uranus and Neptune formed even farther out in the coldest, slowest regions of the disk. They didn't grow fast enough to capture as much gas as Jupiter and Saturn, so they ended up smaller, icier, stranger. And the asteroids, the comets, the Kuiper Belt objects, they're leftovers. Pieces that never quite came together, fragments preserved from the earliest days of the solar system. When we look at protoplanetary disks through 3IATLAS, we're not just seeing alien systems, we're seeing our own past. We're watching the process that created us replayed in 1,000 variations across the galaxy. Here's a mistake we made. For a long time, we assumed planet formation was rare, that it required special conditions, unlikely coincidences. But 3IATLAS is showing us the opposite. Disks are everywhere. Almost every young star has one. And almost every disk shows signs of structure gaps, rings, spirals suggesting planets are forming. Planet formation isn't rare, it's the default. If you have a star, you probably have a disk. If you have a disk, you probably have planets. The question isn't whether planets form, it's what kind of planets form and whether they survive long enough to matter. That's what 3IATLAS is helping us answer. Not by giving us a single answer, but by showing us the full spectrum of possibilities, the outcomes, the variations, the ways things can go right or wrong or somewhere in between. And here's the beautiful part, we're not just passive observers. We're learning. Every disk we study teaches us something new about our own origins. We're learning that the solar system wasn't always stable, that planets migrated, collided, rearranged themselves, that the early solar system was chaotic, violent nothing, like the orderly arrangement we see in the orrery. We're learning that water didn't just appear on Earth. It was delivered, carried by comets and asteroids that formed in the outer solar system, and then migrated inward, crashing into the young Earth, leaving their icy cargo behind. We're learning that moons are common, that many planets, especially giants, capture their own systems of satellites, that these moons can be as complex, as geologically active, as interesting as planets themselves. Every answer raises new questions, but that's not frustrating. That's the point. That's what keeps us looking. So, Picture this: somewhere hundreds of light years away, a young star is surrounded by a disk of dust. The disk is lumpy, irregular, filled with growing planets. One of them, a rocky world, is orbiting in the habitable zone. It's accreting material, growing, differentiating into core mantle crust. Maybe it will develop an atmosphere. Maybe comets will bring water. Maybe billions of years from now, something will live there. Look up, wonder. We can't see that planet yet. It's too small, too dim, buried in the glare of its star. But we can see the gap it's carving, the architecture it's creating, the story it's starting to write. And that's enough. For now, that's enough. Because the real lesson of protoplanetary disks isn't that planets exist. It's that planets are stories. Long, slow, patient stories written in dust and time and gravity. And we're learning to read them one ring, one gap, one spiral at a time. But reading the structure is only part of the puzzle. What about the chemistry? What are these disks made of? What molecules are swirling in the gas, condensing in the ice, building the atmospheres of worlds we'll never touch? Let's turn our attention now to the invisible language written in light. The chemistry of elsewhere. Light carries secrets. Every photon that reaches us has traveled through something gas dust, the thin veil of an atmosphere, and along the way, it's been changed. Absorbed here, scattered there, bent by molecules we can't see but can learn to recognize. This is how we taste distant worlds, not with our tongues but with light. Not by visiting, but by listening to what the photons tell us when they finally arrive. And what they're telling us is, the chemistry of life isn't rare. It's written in the atmospheres of planets we'll never touch. Let's start with something simple. A molecule, water, H2O. Two hydrogen atoms bonded to one oxygen atom, the most familiar chemical compound on Earth. The thing we drink, bathe in, need to survive. But here's what most people don't realize: water has a voice, an infrared voice. When infrared light passes through water, vapor certain wavelengths get absorbed, specific frequencies that correspond to the vibrations of the H2O molecule, the bending of the bond between hydrogen and oxygen, the stretching, the twisting. Each molecule absorbs light at its own unique set of wavelengths. It's like a fingerprint or a barcode. If you know what to look for, you can identify a molecule just by the light it blocks. This is called spectroscopy, and it's how we read the chemistry of alien worlds. We don't need to go there. We don't need to send probes, land rovers, collect samples. We just need to catch the light that passes through their atmospheres, split it into a spectrum, and look for the missing pieces. The dark lines, the absorption features, the fingerprints of molecules floating in alien skies. 3IATLAS isn't just mapping where planets are. It's revealing what they're made of. What molecules are present in protoplanetary disks, what's being locked into forming planets, what will one day become the atmospheres, the oceans, the building blocks of whatever lives there. And the first thing 3IATLAS confirms over and over is this: water is everywhere. Not liquid water, not yet, but water vapor, water ice. Water molecules frozen onto dust grains mixed into the gas embedded in the very fabric of planet formation. In the outer regions of protoplanetary disks beyond the frost line, temperatures drop low enough for water to freeze. Ice coats the dust particles, and as those particles collide and stick together, they carry water with them into planetesimals, into planets, into comets that will one day deliver that water to rocky worlds closer to the star. Earth's oceans didn't form here. They were imported, carried by icy bodies that formed in the colder outer regions of the solar system and then migrated inward, crashing into the young Earth, melting, releasing their cargo. 3IATLAS shows us this process happening in other systems. Water vapor detected in the inner disks, water ice in the outer disks. The same pattern repeated across hundreds of forming solar systems. Water isn't a fluke, it's a feature, a natural outcome of the way disks cool, the way molecules condense, the way chemistry unfolds in the shadow of a young star. But water isn't the only molecule we're detecting. There's also carbon monoxide, CO, a simple molecule, just carbon and oxygen, but incredibly revealing. In protoplanetary disks, CO is abundant. It forms easily in the gas phase, especially in cooler regions. And because it emits strongly in millimeter wavelengths, it's one of the easiest molecules to detect from Earth. By mapping the distribution of CO in a disk, astronomers can measure the disk's temperature, its density, how fast the gas is moving. CO becomes a tracer, a way to visualize the invisible. But CO is also important for another reason: it's a building block. Carbon is essential for organic chemistry for life, as we know it. And CO is one of the primary carriers of carbon in disks. As the disk evolves, CO molecules freeze onto dust grains. They get incorporated into planetesimals. They end up in comets, asteroids, the atmospheres of forming planets. In Earth's early atmosphere, CO was present. It reacted with other molecules, forming more complex compounds. Eventually, through a long chain of chemistry, we're still piecing together those compounds led to amino acids, nucleotides, the precursors of life. When we detect CO in a protoplanetary disk, we're not detecting life, but we're detecting one of the ingredients, one of the possibilities. Then there's methane, CH4, 1 carbon atom, 4 hydrogens. On Earth, methane is produced both geologically and biologically. Volcanoes release it. Bacteria produce it. Cows belch it. In the context of exoplanets, methane is tantalizing, because if you detect methane in an atmosphere, it raises a question: where did it come from? If the planet is a gas giant like Jupiter or Saturn, methane is expected. It forms naturally in the cold, hydrogen-rich atmospheres of these worlds. It's chemistry, not biology. But if the planet is rocky temperate in the habitable zone, and if you detect methane alongside oxygen water, vapor carbon dioxide, then you have to consider the possibility that something is producing it, something alive. Methane doesn't last long in an atmosphere. It breaks down under ultraviolet light. It reacts with oxygen. If you detect it, something must be replenishing it. And on Earth, most of that replenishment comes from life. This is what's called a biosignature, not proof of life, but a hint. A clue that demands further investigation. 3IATLAS helps by showing us which disks have methane, which don't, and where in the disk it's located. Is it in the cold outer regions where methane ice is expected, or is it closer in the warm zones where rocky planets form, where its presence might mean something more? Let's talk about a specific planet, K2-18b. It's about 120 light-years away, orbiting a red dwarf star. It's larger than Earth, about 2.6 times Earth's radius, but smaller than Neptune. Scientists call this a sub-Neptune, a type of planet we don't have in our solar system. In 2019, astronomers announced something remarkable. They had detected water vapor in K2-18b's atmosphere. It was the first time water had been confirmed in the atmosphere of a planet orbiting in its star's habitable zone. The news made headlines. Habitable exoplanet found. Water detected on alien world. The excitement was understandable, but then came the nuance, the complications, the reality that habitable zone doesn't mean habitable. K2-18b probably doesn't have a solid surface. Its atmosphere is likely thick hydrogen-rich, more like a mini Neptune than a super-Earth. The pressures at lower altitudes might be crushing. The temperatures, despite being in the habitable zone, might be too high for liquid water on any hypothetical surface. And yet water is there, methane too. Carbon dioxide, a chemistry that if the planet were smaller, rockier, more Earth-like, might be intriguing. K2-18b teaches us something important. Detecting the right molecules isn't enough. You also need the right context, the right kind of planet, the right kind of star, the right distance, the right mass, the right atmosphere. Chemistry is necessary, but it's not sufficient. Now here's where it gets tricky. How do we actually detect these molecules? How do we measure the composition of an atmosphere on a planet hundreds of light years away? The technique is called transit spectroscopy. And it's elegant, clever, almost too simple to believe. Here's how it works. When a planet passes in front of its star, an event called a transit, the star's light dims slightly. Not much, usually less than 1%, but enough to measure. Now, during the transit, some of the star's light passes through the planet's atmosphere. And as it does, molecules in that atmosphere absorb specific wavelengths. By comparing the spectrum of the star, when the planet isn't transiting to the spectrum during the transit, you can see which wavelengths were absorbed. And from those absorption features, you can identify the molecules. It's like holding a stained glass window up to the sun and figuring out what colors of glass are present based on which colors of light make it through. This technique has been used with the Hubble Space Telescope, the James Webb Space Telescope, and ground-based observatories. It's how we detected water on K2-18b. It's how we've analyzed the atmospheres of dozens of exoplanets. And 3IATLAS contributes by identifying which planets are worth studying, which ones have the right size, the right orbit, the right star, which ones transit so we can actually perform spectroscopy. It's a collaboration. Infrared surveys find the planets. Transit observations reveal their chemistry. But not all planets transit. In fact, most don't. For a planet to transit, it has to pass directly between us and its star. The orbit has to be edge-on from our perspective. If the orbit is tilted even slightly, we'll never see a transit. So, for planets that don't transit, we need other methods. One is called direct imaging. Instead of looking at the star, you block it out using a device called a coronagraph and try to see the planet itself. This is incredibly difficult. Planets are faint, stars are bright. It's like trying to see a firefly next to a searchlight. But in infrared, it gets a little easier because planets emit their own heat. They glow faintly in infrared, especially young planets that are still warm from formation. By observing an infrared blocking out the star's light and taking very long exposures, astronomers can sometimes directly image a planet. And once you have an image, you can take a spectrum. You can measure the planet's infrared emission and identify molecules in its atmosphere. 3IATLAS helps here too, by mapping young systems identifying which ones have planets, which ones have the right brightness and separation to attempt direct imaging. It guides observing campaigns. It tells us where to point the telescopes. Let's talk about carbon dioxide, CO2. On Earth, it's a greenhouse gas. It traps heat. Too much of it and the planet warms. Too little and it freezes. Venus has a thick CO2 atmosphere. It's a runaway greenhouse. Surface temperatures hot enough to melt lead. Atmospheric pressure 90 times that of Earth. A cautionary tale of what happens when a planet gets too much carbon dioxide and loses its water. Mars, on the other hand, has a thin CO2 atmosphere. Most of its atmosphere was lost billions of years ago, stripped away by the solar wind, because Mars doesn't have a strong magnetic field to protect it. CO2 is common in exoplanet atmospheres too. 3IATLAS shows us that carbon dioxide ice exists in the outer regions of protoplanetary disks, just like water ice. As planets form and migrate, they can acquire CO2-rich atmospheres. Whether that's good or bad depends on the details. A little CO2 keeps a planet warm, helps maintain liquid water. Too much and you get Venus, too little and you get Mars. Goldilocks again. Not too much, not too little. Just right. Here's something that surprised scientists: ammonia. NH3, nitrogen and hydrogen. On Earth, ammonia is toxic, reactive, unstable. But in the cold outer regions of protoplanetary disks, it's stable. It condenses into ice. Ammonia has been detected in the atmospheres of Jupiter and Saturn. It's part of the reason their clouds have that banded, colorful appearance. Different layers, different temperatures, different chemical reactions. But ammonia is also interesting. For another reason, nitrogen is essential for life. It's a key component of amino acids, proteins, DNA. Without nitrogen biology, as we know, it doesn't work. On Earth, nitrogen is abundant in the atmosphere. but it's in the form of N2 molecular nitrogen, which is very stable and hard to break apart. Life had to evolve special enzymes, nitrogenases, to convert atmospheric nitrogen into forms that could be used biologically. If ammonia is present on a planet, it provides a more reactive form of nitrogen. It's easier to incorporate into organic molecules. Some scientists suggest that early Earth might have had more ammonia in its atmosphere, making the origin of life a little easier. 3IATLAS helps us map where ammonia is present in forming systems. Whether it's common, whether Earth-like planets are likely to acquire nitrogen-rich atmospheres. The more we learn, the more we realize the chemistry of a planet isn't random. It's shaped by where the planet forms, how it migrates, what it accretes along the way. Now, here's a humbling thought. Everything I've just described, water, methane, CO, CO2, ammonia, these are simple molecules, 2 atoms, 3 atoms, maybe 4. But life on Earth uses far more complex chemistry. Proteins with thousands of atoms, DNA with millions, cells with intricate membranes, organelles, machinery we're still trying to fully understand. We can't detect that complexity remotely, not yet. Even with the most powerful telescopes, even with perfect spectroscopy, we're limited to small molecules, the building blocks, not the structures. So, when we talk about detecting life, we're not talking about seeing cells or organisms. We're talking about detecting anomalies, chemical combinations that don't make sense unless something is actively maintaining them. Oxygen and methane together, for example. On Earth, both are present because life produces them. Plants make oxygen, bacteria make methane. Without life, one would react with the other and disappear. If we detect both in an exoplanet atmosphere in significant amounts stable over time, it's not proof of life, but it's a signal, a reason to look closer, a possibility worth investigating. There's a concept in astrobiology called false positives, a biosignature that looks like life but isn't. Oxygen, for example. On Earth, almost all atmospheric oxygen comes from photosynthesis. Life made it. But oxygen can also be produced abiotically. Water molecules can be split by ultraviolet light, a process called photodissociation. The hydrogen escapes to space. The oxygen lingers. If a planet has a lot of water vapor and a very active star, it might accumulate oxygen without life, a false positive. Methane, too. It can be produced by geological processes, volcanic activity, reactions between rock and water. This is why context matters. This is why we need to understand not just the chemistry, but the planet's size, its star, its history. We need to rule out the false positives before we can claim the real thing. 3IATLAS gives us that context. By studying hundreds of systems, we learn what's normal, what's expected, what's unusual. If we find a planet with oxygen and methane, and we know its star isn't active enough to photolyze water, and we know its geology isn't active enough to produce methane, then maybe we've found something. Do you ever wonder what it would feel like to breathe an alien atmosphere? Not that you could, most would kill you instantly. But imagine standing on a rocky world, looking up at a sky that's not blue, but orange or purple or green. A sky filled with different molecules scattering light in different ways. On Earth, the sky is blue because nitrogen and oxygen scatter short wavelengths of light more efficiently than long wavelengths. Blue light bounces around, red light passes through. But on a planet with a different atmospheric composition, the sky could be any color. A methane-rich atmosphere might scatter red light, making the sky look rusty. A thick haze of organic molecules might scatter all wavelengths, equally making the sky gray or brown. The sunsets would be different too. On Mars, because the atmosphere is thin and dusty, sunsets are blue, the opposite of Earth. On a planet orbiting a red dwarf, the star itself is cooler, dimmer, redder. Even with an Earth-like atmosphere, the daylight would feel different, softer, dimmer, like perpetual twilight. Chemistry shapes not just whether a planet can support life, but what life would experience, the color of the sky, the quality of the light, the feel of the air. Here's the lesson 3IATLAS keeps teaching us. Diversity is the rule, not the exception. Every disk is different. Every planet is different. Every atmosphere is different. We've found planets with clouds made of silicate glass, planets where it rains molten iron, planets with atmospheres so thick you couldn't see the surface even if you were standing on it. We've found planets that lost their atmospheres entirely stripped by stellar winds, planets that never had atmospheres to begin with. The universe is not giving us copies of Earth. It's giving us variations, experiments, a million different ways to make a world. And somewhere in that diversity, probably there's life. Maybe not like ours. Maybe not carbon-based, water-loving, oxygen-breathing, but something. Some chemistry that's found a way to persist, to replicate, to adapt. We're learning the language slowly, one spectrum at a time. And the more we learn, the more we realize the question isn't whether the universe has the ingredients for life. It's whether life has learned to use them. We'll keep looking, keep listening, keep reading the light that travels across the dark. Because the chemistry of elsewhere is also the chemistry of here. We're made of the same atoms, forged in the same stars, scattered by the same processes. If water is everywhere, if carbon is everywhere, if the building blocks are everywhere, then maybe we're not as alone as we thought. Or maybe we are. Maybe life is so improbable, so delicate that even with all the right ingredients, it almost never happens. Either answer is staggering, but knowing the chemistry, that's the first step. And 3IATLAS is guiding us, molecule by molecule, toward understanding. Now, let's narrow our focus. Let's talk about the zone where all of this matters most. The distance from a star where water can be liquid, where temperatures are just right, where life, if it exists, has the best chance of surviving, the habitable zone. But as we'll see, habitable is a more complicated word than it seems. There's a distance from every star where water can exist as a liquid, not ice, not vapor, liquid, pooling in valleys, flowing in rivers, filling oceans. It sounds simple, a sweet spot, a zone where life as we know it could begin. We call it the habitable zone, the Goldilocks zone. Not too hot, not too cold, just right. But here's the paradox: being in the right place doesn't guarantee the right outcome. You can have all the ingredients and still end up with nothing. Or worse, something that looks perfect from a distance but hostile up close. The universe doesn't owe us copies of Earth. And the more we look, the more we realize habitable is a word that hides 1,000 complications. The concept of the habitable zone is old, older than exoplanet science. In the 1950s, scientists started asking, if we want to find life elsewhere, where should we look? The answer seemed obvious. Life needs water. Water is liquid between 0 and 100 degrees Celsius at Earth's surface pressure. So you calculate the distance from a star where temperatures fall in that range. For the Sun, the habitable zone extends roughly from Venus's orbit to Mars's orbit. Earth sits comfortably in the middle. For hotter, brighter stars, the zone is farther out. For cooler, dimmer stars, it's closer in. It's elegant, mathematical, a simple rule to guide the search. But then, we started finding actual planets. And the rules started breaking. The first exoplanets discovered weren't in habitable zones. They were hot Jupiters, gas giants orbiting closer to their stars than Mercury is to the Sun. Planets that shouldn't exist according to our models, but there they were blazing in the data. Then we found super-Earths, planets larger than Earth but smaller than Neptune. Some in the habitable zone, some not. Some rocky, some gassy, some with thick atmospheres, some with none. And with each discovery, the question got harder. What does habitable actually mean? Does it mean liquid water exists or that life exists? Because those are very different things. Venus is technically in the Sun's habitable zone, but its surface is 465 degrees Celsius. hot enough to melt lead. Its atmosphere is 90 times thicker than Earth's, made mostly of carbon dioxide, with clouds of sulfuric acid. Nothing we know could live there, and yet by the distance criterion, it's habitable. Mars is also in the zone, but it's cold, dry, and nearly airless. Its atmosphere was stripped away billions of years ago. Any water that remains is locked in ice at the poles or buried underground. Life might have existed there once. Maybe it still does deep below the surface. But Mars today is not a haven. It's a frozen desert. So, the habitable zone isn't enough. Distance is just the starting point. You also need the right kind of planet, the right kind of atmosphere, the right kind of star. Let's talk about stars, because not all stars are like the sun. The sun is a G-type star, medium-sized, medium-temperature stable. It's been burning steadily for 4.5 billion years, and it will keep burning for another 5 billion. But most stars in the galaxy aren't like the sun. About 75% are red dwarfs, M-type stars, smaller, cooler, dimmer. Red dwarfs burn their fuel so slowly that they can last for trillions of years. They're the longest-lived stars in the universe. Some of the red dwarfs that exist today will still be shining long after the sun has died. And because they're so common, they're statistically the most likely stars to host planets. If you want to find life, you'd think red dwarfs would be the place to look. But there's a problem. Red dwarfs are active, violent. They produce frequent stellar flares, bursts of radiation, and charged particles that blast into space. And because the habitable zone around a red dwarf is so close to the star, any planet in that zone gets hit hard. Take Proxima Centauri b, the closest exoplanet to Earth, only 4 light-years away. It orbits Proxima Centauri, a red dwarf, and it sits right in the middle of the habitable zone. When it was discovered in 2016, the excitement was palpable. A potentially habitable world practically next door. Maybe we could send a probe, maybe we could study it in detail, maybe there's life there. But then the data came in. Proxima Centauri is a flare star. It erupts regularly, sometimes increasing in brightness by several times in just minutes. These flares emit X-rays, ultraviolet radiation, high-energy particles, all of it aimed at Proxima b. Scientists ran simulations. They calculated how much radiation the planet receives. And the conclusion was sobering. Unless Proxima b has a strong magnetic field to deflect the stellar wind, its atmosphere has probably been stripped away. No atmosphere means no liquid water. No liquid water means no life, at least not on the surface. Proxima b might be in the habitable zone, but it's probably not habitable. This is the Goldilocks paradox. You can be in the right place and still be the wrong planet. Earth isn't habitable just because it's the right distance from the sun. It's habitable because it has a magnetic field generated by a molten iron core that shields it from the solar wind. Because it has plate tectonics, which recycle carbon and regulate the climate. Because it has a large moon, which stabilizes its axial tilt and prevents wild climate swings. Remove any one of those factors, and Earth might be as lifeless as Venus or Mars. So, when we say a planet is in the habitable zone, we're not saying it's habitable. We're saying it has a chance, a possibility, if everything else goes right. 3. The Atlas helps us understand this. By mapping the environments around different types of stars, it shows us which systems are calm, which are chaotic, which planets are likely to retain their atmospheres, which are likely to lose them. Red dwarfs, despite their abundance, might not be the best places to look for life. Not because they're inherently hostile, but because their planets face challenges that Earth-like worlds around sun-like stars don't. But that doesn't mean we should ignore them. It means we need to be more selective. Look for red dwarfs that are older, less active. Look for planets with strong magnetic fields. Look for systems where the odds are better. Now let's talk about size, because the size of a planet matters just as much as its distance from the star. Earth is small, rocky. It has a thin atmosphere held in place by gravity, but not so thick that it traps all the heat. The surface pressure is just right for liquid water. But if you make a planet bigger, say twice Earth's radius, things change. The planet's gravity increases. It can hold on to lighter gases like hydrogen and helium. Its atmosphere becomes thicker, heavier, more like a gas giant than a terrestrial world. These are called mini-Neptunes, and they're incredibly common, more common in fact than Earth-sized planets. But here's the problem. We don't know what mini-Neptunes are like. We don't have one in our solar system. We don't know if they have solid surfaces beneath their thick atmospheres or if they're just gas all the way down. We don't know if life could exist there or if the crushing pressures and choking atmospheres make it impossible. Some mini-Neptunes orbit in the habitable zone, and when we detect water vapor in their atmospheres, it's tempting to call them habitable. But water in the atmosphere doesn't mean oceans on the surface. It might just mean thick clouds. Perpetual rain, no land, no surface, no place for life to anchor. Here's a case study, TOI 270d. A mini-Neptune about 70 light-years away, orbiting in the habitable zone of a red dwarf. It's about 2.4 times the size of Earth. In 2023, the James Webb Space Telescope analyzed its atmosphere, and the results were strange. The planet has water vapor, carbon dioxide, methane, but the methane concentrations are far higher than expected. Scientists suggest the planet might be what's called a Hycean world, a planet with a global ocean beneath a thick hydrogen atmosphere. Deep beneath the clouds, where the pressure is immense but the temperature is moderate, liquid water might exist. Could life exist there? Maybe. In the ocean below, the crushing atmosphere in the dark under pressures we can barely imagine. Maybe. But it wouldn't be life like ours. It would be something stranger, adapted to conditions we've never encountered. TOI 270d is in the habitable zone, but it's not a second Earth. It's something else entirely. Let's return to Earth for a moment, because Earth is habitable now, but it wasn't always. 4 billion years ago, Earth's atmosphere had almost no oxygen. It was mostly nitrogen, carbon dioxide, methane. The sun was 30% dimmer than it is today. By all rights, Earth should have been frozen solid, but it wasn't. It was warm enough for liquid water, warm enough for life to emerge. How? The greenhouse effect. Carbon dioxide and methane trapped heat. The young Earth's atmosphere was thick with greenhouse gases, and that kept the planet warm despite the weak sun. Over time, photosynthetic bacteria evolved. They consumed carbon dioxide and released oxygen. Slowly, over billions of years, the atmosphere changed. Oxygen levels rose. Carbon dioxide levels dropped. The planet cooled slightly, but by then, the sun had brightened, compensating. Earth's habitability wasn't static. It evolved. It was maintained by life itself. This is called the Gaia hypothesis. The idea that life doesn't just inhabit a planet, it regulates it. It keeps conditions stable, livable through feedback loops we're only beginning to understand. If that's true, then habitability isn't just about being in the right zone. It's about staying there, maintaining the balance, and that might require life. Which raises a troubling question: can a planet become habitable without life? Or does habitability require life to maintain it? Here's another mistake we make. We assume habitable zones are fixed, but they're not. They move. As stars age, they get brighter. The sun is about 10% brighter now than it was when Earth formed. In another billion years, it will be bright enough that Earth's oceans will start to evaporate. The habitable zone will shift outward, leaving Earth behind. Mars, which is too cold now, might warm up. Its ice might melt. It might briefly become habitable. And then the sun will keep brightening. It will swell into a red giant. The habitable zone will move out past Jupiter, past Saturn. Earth will be incinerated. Mars will be incinerated. But maybe for a few million years, some of Jupiter's moons, Europa Ganymede, will have liquid water on their surfaces. The habitable zone is a moving target, and planets don't move with it. They stay where they are, orbiting at fixed distances, while the zone drifts past them. So being in the habitable zone today doesn't mean you'll be in it forever. and being outside it today doesn't mean you always were. 3IATLAS shows us systems at different stages of evolution. Young stars with wide, cool, habitable zones. Middle-aged stars like the Sun. Old stars whose zones have shifted, leaving their inner planets scorched. And by studying these systems, we learn something humbling: habitability is temporary, fleeting. A narrow window in a planet's history when conditions are just right. Earth has been in that window for billions of years, but it won't last forever. And most planets, even if they enter the window, don't stay there long. Now let's talk about moons, because moons can be habitable too. Europa, one of Jupiter's moons, is covered in ice. But beneath that ice, scientists believe is a global ocean. Liquid water kept warm by tidal heating, the flexing of Europa's interior caused by Jupiter's gravity. Europa is far outside the Sun's habitable zone. It's cold, frozen, lifeless on the surface. But below, maybe not. The same is true for Enceladus, one of Saturn's moons. It has geysers that shoot water vapor into space sourced from a subsurface ocean. That ocean might be habitable. It has water energy chemistry. If moons can be habitable, then the number of potentially habitable worlds in the galaxy skyrockets. Because gas giants are common, and gas giants have moons. 3IATLAS might not detect those moons directly, they're too small, too faint. But by mapping where gas giants form, where they migrate to, it gives us clues about where habitable moons might exist. There's a concept called optimistic versus conservative habitable zones. The conservative zone is narrow. Only planets where liquid water is definitely stable. The optimistic zone is wider. It includes planets where liquid water might be stable under the right conditions. Earth is in both. Mars is in the optimistic zone, but not the conservative one. Venus might have been in the optimistic zone early in its history before the runaway greenhouse effect took over. When scientists count habitable planets, the number varies depending on which definition you use. Conservative estimates say there might be billions of habitable planets in the galaxy. Optimistic estimates say tens of billions. But here's the truth, we don't know which definition is right. Because we don't know what the minimum requirements for life are. We don't know how flexible life can be. We don't know if Earth is average or exceptional. Maybe life needs everything Earth has: magnetic field plate tectonics, large moon, stable star. In that case, habitable planets are rare. Or maybe life is tougher than we think. Maybe it can survive in thin atmospheres under ice in the crushing depths of mini Neptune oceans. In that case, habitable planets are everywhere. We won't know until we find life, or keep searching and don't. Here's what I want you to think about. You're lying here, warm, breathing air that's 21% oxygen under a magnetic shield. You can't see on a planet that's the right size, the right distance, with the right moon, the right core, the right history. How many things had to go right for you to be here? Not just evolutionary things, not just the emergence of life, the development of intelligence, the rise of civilization, but geological things, cosmic things. The formation of the solar system in a calm region of the galaxy, the sun being the right type of star, Jupiter's gravity sweeping up asteroids that might have hit Earth too often, the moon stabilizing Earth's tilt. Every one of those is a variable, a roll of the dice, and Earth came up lucky every time. Does that mean Earth is rare, or does it mean we're only noticing the variables because we're here? Because if any of them had been different, we wouldn't exist to ask the question. It's called the anthropic principle, and it's maddening because it doesn't tell us if we're alone or common. It just tells us that we're biased observers. 3IATLAS can't answer that question, but it can show us the range of possibilities. The planets that are too hot, too cold, too big, too small, too close to violent stars, too far from calm ones. And somewhere in that range, maybe there's another world, not like Earth, not a copy, but habitable in its own way, with its own chemistry, its own climate, its own story. Or maybe there isn't. Maybe Earth is the only one, the only roll of the dice that came up sixes every time. Either way, the search continues, because the question matters, because knowing whether we're alone changes everything, and because even if we don't find life, we'll find something just as profound: the limits of habitability, the edges of the Goldilocks zone, the line between possible and impossible, and that's worth knowing too. So, we keep looking, keep mapping, keep refining our understanding of what habitable really means. Because perfect isn't a place, it's a balance, a convergence of unlikely factors, a moment in time when everything aligns. And the universe is full of moments. Some last billions of years, some last a blink. We're in one of those moments now. Let's see how many others we can find. But distance and chemistry and stable zones, they're only part of the story. Some planets don't stay where they formed, they move. They migrate inward, outward, dragging chaos in their wake. And when planets migrate, solar systems transform. Let's follow those wanderers now. The giants that refuse to stay in place. Imagine a world the size of Jupiter, but so close to its star that its year lasts only 3 days. So close that its atmosphere is being stripped away, molecule by molecule. So close that one side is perpetually scorched, while the other freezes in shadow. These planets exist, hundreds of them, and they shouldn't. According to everything we thought we knew about how solar systems form, gas giants belong far from their stars, out in the cold. Not here, not in the fire. But the universe doesn't follow our rules, and these wandering giants, these hot Jupiters, have a story to tell. A story of migration, violence, and survival. Let's go back to 1995, October 6th. Two Swiss astronomers, Michael Mayor and Didier Queloz, announced something extraordinary. They'd found a planet orbiting a sun-like star called 51 Pegasi. It was the first confirmed exoplanet around a normal star, the discovery that changed everything. But the planet itself was baffling. It was massive, about half the mass of Jupiter, but it orbited incredibly close to its star, closer than Mercury is to the Sun. Its orbital period was just 4.2 days. Astronomers called it a hot Jupiter, and at first, many refused to believe it was real. It violated the models. Gas giants couldn't form that close to a star. The temperatures were too high. The disk material would have been blown away before planets could coalesce. It had to be a mistake, an error in the data, something misunderstood. But then more were found. Dozens, then hundreds. Hot Jupiters weren't anomalies. They were common, and that meant our understanding of planetary formation was incomplete, maybe even wrong. Here's the problem. Gas giants form in the outer regions of protoplanetary disks beyond the frost line, where it's cold enough for ice to exist. The solid cores of these planets, made of rock and ice, grow large enough to gravitationally capture hydrogen and helium from the surrounding gas. This process takes time, millions of years, and it requires a lot of material. Hydrogen and helium are abundant in the outer disk, but sparse in the inner regions where the heat from the star has blown most of it away. So gas giants can't form close to their stars. The conditions aren't right. The material isn't there. But hot Jupiters are there, orbiting at distances where they couldn't have formed. The only explanation: they didn't form there. They formed farther out in the cold where gas giants belong. And then somehow they moved inward. This is called planetary migration, and it rewrote the textbooks. How does a planet migrate? It sounds impossible. Planets are massive. They're locked in their orbits by gravity. How do they just move? The answer lies in the disk. Remember, young planets are embedded in protoplanetary disks, vast clouds of gas and dust. And that gas exerts forces on the planet. As the planet orbits, it creates density waves in the disk, spiral patterns like the wake behind a boat. Those waves push back on the planet, creating drag. And that drag causes the planet to lose energy. Slowly over time, its orbit shrinks. It spirals inward. This is called Type 2 migration. And for large planets, Jupiter mass and above, it's incredibly efficient. Within a few 100,000 years, a planet that formed at Jupiter's distance could migrate all the way to Mercury's distance. Or closer, much closer. Some hot Jupiters orbit so close to their stars that their atmospheres are boiling away. Their surfaces, if they have surfaces, are molten. They're being consumed bit by the very stars they orbit. Here's where it gets tragic. When a gas giant migrates inward, it doesn't travel alone. It disrupts everything in its path. Imagine a forming solar system. Rocky planets are beginning to coalesce in the inner regions. Planetesimals are colliding, growing, settling into stable orbits. It's chaotic, but it's organized chaos. Structure is emerging. Then a giant planet starts migrating inward. Its gravity is immense. It scatters the smaller bodies. Some are flung into the star. Some are ejected into interstellar space. Some are pushed into highly eccentric orbits where they collide with each other, fragmenting into dust. The inner solar system is destroyed, and the gas giant keeps moving, oblivious, dragging destruction in its wake. By the time the giant reaches the inner edge of the disk, where it finally stops, either because the disk has dispersed or because tidal forces from the star halt its inward motion, there's nothing left. No rocky planets, no habitable zone worlds. Just the giant alone in the fire. 51 Pegasi b, that first hot Jupiter, probably did this. It probably destroyed an entire inner solar system. Maybe there were planets there. Maybe some of them were in the habitable zone. Maybe they never got the chance to develop atmospheres, oceans, life. We'll never know, because they're gone, scattered, consumed. This is the loneliness of hot Jupiters. They're survivors in a sense, but they're also destroyers. They ended the story before it could begin. And 3IATLAS shows us that this happens often. Many systems have hot Jupiters, and in those systems there are no rocky planets close to the star. The inner regions are empty, cleared out. It's a reminder not all solar systems are hospitable to life. Some are battlegrounds, and the giants won. But here's the twist. Not all migrating giants end up as hot Jupiters. Some stop halfway, some reverse course. Our solar system is an example. Jupiter migrated inward early in the solar system's history. Scientists suggest it moved from about 5.2 AU, its current distance, to about 1.5 AU, roughly where Mars is now. As it migrated, it scattered planetesimals. It disrupted the forming terrestrial planets. It could have destroyed everything. But then something remarkable happened. Saturn formed. And as Saturn grew, it began to migrate too. Its gravity interacted with Jupiter's. The two planets became locked in a resonance, a gravitational dance. And together, they migrated outward, back toward their original positions, away from the inner solar system. This is called the Grand Tack hypothesis. Tack, as in tacking a sailboat changing direction. If it's true, then Jupiter and Saturn saved the inner solar system. By migrating outward, they left enough material behind for Earth, Venus, Mars, and Mercury to form. They stopped short of destroying us. We owe our existence to a reversal, a cosmic accident, a moment when two giants change course. Not every system is so lucky. 3IATLAS reveals systems where migration continued unchecked. Systems with multiple hot Jupiters stacked close to their stars, their orbits intertwined. Systems where the giants never stopped, where nothing else survived. And it reveals something else: migration can take different forms. Type Y migration affects smaller planets, super-Earths, mini-Neptunes. They migrate faster than giants because they're less massive. They can't open wide gaps in the disk. They just drift inward, pulled by the gas. Some super-Earths end up very close to their stars, orbiting in days or even hours. They're scorched, airless, rocky cores with no chance of habitability. These are sometimes called super-Mercuries, worlds that formed farther out, migrated inward, and ended up in the furnace. There's another mechanism too. Gravitational interactions between planets. Scattering. Imagine a system with 2 or 3 giant planets. They form in the outer disk all relatively close to each other. At first, their orbits are stable, but over time, small perturbations accumulate. One planet pulls on another. Orbits shift. Eccentricities grow. Eventually, the system becomes unstable. The planets' orbits cross. They have a close encounter. And in that encounter, one planet gains energy and moves outward. The other loses energy and moves inward. The inward-moving planet can end up on a highly eccentric orbit swooping close to the star and then swinging far out. Over time, interactions with the disk or tidal forces from the star can circularize the orbit, turning it into a hot Jupiter. The outward-moving planet, meanwhile, might be ejected entirely, flung into interstellar space, a rogue planet wandering the galaxy, orphaned from its star. 3IATLAS finds evidence of both. Hot Jupiters on circular orbits suggesting slow migration through the disk, and hot Jupiters on eccentric orbits suggesting violent scattering events. Each system tells a different story. Each giant took a different path. Let's talk about a specific system. WASP-12. It's about 400 light-years away. The planet WASP-12b is a hot Jupiter, but it's one of the most extreme ever found. It orbits its star in just 1.1 days. Its surface temperature is over 2,500 degrees Celsius, hot enough to vaporize iron, hot enough that the planet is being torn apart. The star's gravity is pulling on the planet, stretching it into an egg shape. Material from the planet's atmosphere is streaming toward the star, forming a glowing arc. The planet is literally being devoured. Scientists estimate that WASP-12b will be completely consumed within 10 million years. In cosmic terms, that's a blink, a moment. WASP-12b migrated too close. It stopped too late. And now it's paying the price. It's a cautionary tale. Migration isn't always survival. Sometimes it's a slow death. But not all hot Jupiters are doomed. Some are stable. Some have been orbiting close to their stars for billions of years, and they'll continue for billions more. The difference is tidal locking. When a planet orbits very close to its star, the star's gravity pulls more strongly on the near side than the far side. Over time, this tidal force slows the planet's rotation until one side always faces the star. The planet becomes tidally locked, one hemisphere in perpetual day, the other in perpetual night. On the day side, temperatures soar. The atmosphere heats up, expands, rises. On the night side, temperatures plummet. The atmosphere cools, contracts, sinks. This creates powerful winds. Jets of gas flowing from the day side to the night side, trying to balance the temperature difference. The fastest winds in the solar system on Jupiter reach about 640 kilometers per hour. On hot Jupiter's winds can exceed 10,000 kilometers per hour. Imagine standing on one of these worlds if you could. The wind would be a constant roar. The sky would be dark on one side, blazing on the other. And the heat, unbearable, unimaginable. But life adapts. At least on Earth, life has found ways to survive in deserts and deep oceans, in volcanic vents, in frozen tundras. Could it adapt to a hot Jupiter? Probably not. The temperatures are too extreme, the radiation too intense, the winds too violent. But maybe in the upper atmosphere where pressures are lower and temperatures more moderate, some kind of airborne life could exist, floating, never touching a surface. It's speculation. But it's a reminder we don't know the limits of life. We only know the limits of life as we understand it. Here's a question for you. If you could visit one of these migrating giants, which moment would you choose? The beginning, when it first started moving inward, carving gaps in the disk, scattering planetesimals. The middle, when it was surrounded by debris, a giant in a storm of its own making. Or the end, when it settled into its final orbit alone, with nothing left to destroy. Each moment would tell you something different about the nature of planetary systems, about creation and destruction, about survival and loss. 3IATLAS doesn't just show us the end states, it shows us the evidence of migration. The empty inner regions, the asymmetrical disks, the gaps that are too wide, too clean, suggesting a planet passed through and cleared everything out. It shows us systems in transition, planets still migrating, disks still full of gas, still exerting drag. And by studying these systems at different stages, we piece together the full story. The narrative of how gas giants are born in the cold, wander through the fire, and either survive or perish. It's not a single story, it's 1,000 stories, each one slightly different, each one shaped by timing, by chance, by the specific conditions of that disk, that star, that moment. Our solar system could have been very different. If Jupiter had migrated all the way inward, Earth wouldn't exist. If Saturn hadn't formed when it did, the Grand Tack wouldn't have happened. If the disk had been more massive or less massive, or if the timing had been off by even a little, the inner solar system would be empty, or crowded with giants, or something in between. We're here because of a specific sequence of events, a specific chain of migrations and reversals, a story that could have gone 100 other ways. And the systems we see through 3I-ATLAS, the ones with hot Jupiters, the ones with scattered debris, the ones with empty inner regions, those are the other ways. The paths not taken, the stories that ended differently. Here's the humbling part. We don't know how common Earth-like solar systems are. We know hot Jupiters are common. We know migration is common. We know destruction is common. But systems like ours, where the giants stayed in the outer regions, where the inner regions were left intact, where rocky planets had a chance to form and thrive, how common are those? Maybe very common. Maybe migration usually stops halfway like Jupiter's did. Maybe most systems end up stable with giants in the outer regions and terrestrial planets in the inner regions. Or maybe we're rare. Maybe the Grand Tack was an unlikely event. Maybe most giants migrate all the way inward, leaving nothing behind. We don't know yet, but 3I-ATLAS is helping us find out. System by system, giant by giant, story by story. Think about this as you drift. Somewhere light years away, a gas giant is migrating, slowly, inexorably, moving inward through the disk, its gravity pulling on everything around it. Maybe there's a rocky planet in its path, a world that was just starting to form, a clump of rock and ice growing larger, accreting material on its way to becoming something. And the giant arrives, and the rocky world is scattered, flung into a different orbit, or into the star, or out into the dark. Its story ends before it begins. But somewhere else in another system, another giant stops. It reverses, it moves outward, and the rocky worlds survive. They grow, they develop atmospheres, oceans, maybe one day life. The difference between those two outcomes is chance, timing, the presence or absence of a second giant, the density of the disk, the age of the star. Everything matters. Every variable tips the balance, and we're the result of a balance that tipped in our favor. But not every planet is so fortunate. Some are left behind not by migrating giants, but by time itself. Collisions, fragmentations, the slow grinding of gravity. When worlds don't survive, they leave something behind. Dust, debris, the ghosts of what might have been. Let's turn our attention now to those remnants, the rings of broken worlds. There's a ring of dust around a distant star, thin, faint, almost invisible. If you didn't know to look for it, you'd miss it entirely. But it's there, orbiting quietly, glowing softly in infrared. It's not a protoplanetary disk. The star is too old for that. The gas is gone. The planets, if they formed, have already finished forming. So, what is it? Where did this dust come from? The answer is simple and haunting. Something broke. A planet, an asteroid, a moon. Something collided, shattered, and left this ring behind. A memorial, a scar, the ghost of a world that used to be. These are called debris disks, and they're everywhere. Our solar system has them too. The asteroid belt between Mars and Jupiter, the Kuiper belt beyond Neptune. Both are debris leftover material from the solar system's formation, mixed with fragments from collisions that happened later. Every time an asteroid smashes into another asteroid, dust is released. Every time a comet passes close to the sun and sublimates, it leaves a trail of ice and rock. That material doesn't disappear. It spreads out, forming thin rings around the sun. From a distance, if an alien civilization pointed a telescope at our solar system, they'd see those rings, faint, dusty. And they'd know this system has had collisions. Things have broken here. 3IATLAS maps these debris disks around other stars, hundreds of them. And each one tells a story of violent survival and what happens after the planets are done forming. Let's start with the basics. A debris disk forms when a protoplanetary disk runs out of gas. The hydrogen and helium are blown away by stellar winds or simply dissipate over time. What's left are solid objects, planets, planetesimals, asteroids, comets. These objects continue to orbit, but space isn't empty. Orbits cross. Gravitational perturbations nudge things off course. Collisions happen. When two rocky bodies collide, they fragment. The impact releases energy heat shock waves. Pieces fly apart. Some are large kilometers across. Some are small dust grains, barely microns wide. The dust doesn't fall back together. It doesn't reform into a planet. It's too dispersed, too low in mass. Instead, it spreads out into a ring orbiting the star where the collision happened. Over time, radiation pressure from the star pushes the smallest grains outward. They spiral away, lost to interstellar space. Larger grains stay in orbit longer, but eventually they collide again, fragmenting further, creating more dust. It's a cycle. Collisions create dust. Dust spreads out. More collisions create more dust. The disk persists for millions, sometimes billions of years. But it's not a protoplanetary disk. It's not building anything. It's the aftermath, the rubble, the evidence that something was here and now it's broken. Our solar system's asteroid belt is a debris disk of sorts. But it's not the result of a single planet breaking apart. It's the result of a planet that never formed. In the early solar system, material between Mars and Jupiter should have coalesced into a planet. But Jupiter's gravity was too strong. It stirred up the region, increasing collision velocities. Instead of sticking together, planetesimals shattered on impact. The asteroid belt is what's left. Fragments. Millions of them ranging in size from Ceres, about 940 kilometers across, down to grains of dust. The total mass of the asteroid belt is less than Earth's moon. It's almost nothing, but it's still there, still orbiting, still colliding. Still creating dust. From another star looking at the sun, an alien astronomer would see a faint infrared glow around Jupiter's orbit. They'd detect dust, and they'd infer something happened there. Something didn't finish forming. 3IATLAS shows us debris disks with structure, not just smooth rings, but clumps, gaps, asymmetries. And those features are clues. Take Fomalhaut. It's a bright star about 25 light-years away, twice the mass of the sun. In the 1980s, infrared observations revealed it had a debris disk. In 2004, Hubble took an image and the structure was stunning. The disk wasn't centered on the star. It was off to one side, lopsided, and it had a sharp inner edge as if something had carved a boundary. Astronomers realized there must be a planet. A massive planet orbiting inside the disk, its gravity shepherding the dust, keeping it confined to a narrow ring. In 2008, Hubble detected a faint point of light moving through the disk. They called it Fomalhaut B. It was hailed as the first exoplanet directly imaged in visible light. But then, in 2020, the planet disappeared. Follow-up observations showed nothing. No point of light, no planet. What happened? Scientists now suggest that Fomalhaut B wasn't a planet at all. It was a cloud of dust, the aftermath of a collision between two large asteroids. The impact released so much debris that it briefly appeared as a bright object. But over time, the dust dispersed and the planet faded. Fomalhaut b was a ghost. A momentary flare in the debris disk. A collision caught in the act. Here's what that tells us. Debris disks aren't static, they're active. Things are still happening. Collisions, fragmentations. The slow grinding of a solar system that's still settling, still reshaping itself. Our solar system is 4.5 billion years old, but it's not done. The asteroid belt still has collisions. The Kuiper belt still has objects smashing into each other. Every few years, we see a new comet, a fragment from the outer solar system, nudged onto a trajectory that brings it close to the sun. In a few billion years, some of those collisions will create enough dust to make the solar system's debris disk brighter, more noticeable. And an alien astronomer watching from afar might see a spike in infrared emission and think something big just happened there. Let's talk about Beta Pictoris. It's one of the most studied debris disks discovered in 1984. It's about 63 light-years away, and it's young only about 20 million years old. Beta Pictoris has a massive debris disk, edge-on from our perspective, so we see it as a thin line of light extending far from the star. It's bright, prominent, full of dust. But it's not just dust. In 2008, astronomers detected a planet Beta Pictoris b, a gas giant about 10 times the mass of Jupiter orbiting inside the disk. In 2019, they detected a second planet Beta Pictoris c, closer to the star. These planets are sculpting the disk. Their gravity creates gaps, warps the structure, flings debris into new orbits. Beta Pictoris is a solar system in progress. The planets are still clearing their paths, still sweeping up material, still causing collisions. And here's the fascinating part. Beta Pictoris also has comets, lots of them. Observations have detected transient absorption lines, brief dips in the star's light, caused by gas from evaporating comets passing in front of the star. These comets are being flung inward by the gravity of the planets. It's like a replay of the late heavy bombardment in our solar system, when Jupiter and Saturn's migrations sent a barrage of comets and asteroids toward the inner planets. Earth was hit, the moon was hit, it was violent, chaotic, transformative. Beta Pictoris is going through that now, and we're watching it happen. Debris disks also tell us something important. Collisions are inevitable. Even after planets form, even after the gas dissipates, the solar system isn't stable. It's just less chaotic. Earth's moon formed from a collision. About 4.5 billion years ago, a Mars-sized object called Theia crashed into the early Earth. The impact was catastrophic. It vaporized rock, melted the surface-flung debris into orbit. That debris coalesced into the moon. For a time, Earth would have been surrounded by a debris disk, a ring of molten rock and dust glowing in the infrared, slowly gathering into a single large satellite. If an alien civilization had been watching with something like 3IATLAS, they would have seen the collision. They would have seen the spike in infrared emission. They would have seen the disk form then clear as the moon took shape. They would have known something violent just happened there, and the system would never be the same. Here's a question. How many Earths have been destroyed in collisions? How many rocky planets in the habitable zones of distant stars were just starting to develop atmospheres, just beginning to cool, just on the verge of becoming something, and then got hit? We don't know, but debris disks give us hints. The brighter the disk, the more recent the collision. The more asymmetric the structure, the more likely a planet is involved stirring things up. 3IATLAS finds systems with bright, massive debris disks. Systems where collisions are frequent. Systems where planets are still in danger. And it finds systems like ours where the disk is faint, sparse, mostly cleared. Systems that have reached a kind of equilibrium, where the big collisions are over and what's left is just the cleanup. There's a star called HD 1725555, about 95 light-years away. In 2009, astronomers detected something unusual in its infrared spectrum. Glass, vaporized rock, silicon monoxide gas. These aren't normal components of a debris disk. They're the byproducts of an extreme impact, something hot, violent, recent. Scientists suggest that within the past few thousand years, a blink in cosmic terms, two planets collided at HD 1.255, not just asteroids, planets. One of them was probably the size of Earth, maybe larger. The impact vaporized the crust. It melted the mantle. It released so much energy that the resulting debris is still glowing, still cooling, still radiating heat into space. If there was life on either of those planets, it's gone now, incinerated, scattered, reduced to glass and dust. HD 1.255 is a reminder planetary systems are fragile. Collisions don't just happen in the early stages. They can happen anytime. And when they do, entire worlds can be erased. But collisions aren't always destructive. Sometimes they're creative. Earth's moon is the result of a collision. And the moon stabilizes Earth's axial tilt, prevents wild climate swings, creates tides that may have been essential for the development of life. Without that collision, Earth would be different, maybe less habitable, maybe not habitable at all. Collisions deliver water. Comets and asteroids from the outer solar system, rich in ice, crash into rocky planets, leaving their cargo behind. Earth's oceans are in part the result of impacts. Collisions mix materials. They bring volatile elements from the outer regions to the inner regions. They redistribute chemistry, creating diversity. So debris disks aren't just graveyards, they're laboratories. Places where the ingredients for life are being shuffled, rearranged, tested. 3IATLAS helps us identify which debris disks are old, settled quiet, and which are young, active, still experiencing major collisions. The young ones are brighter, more massive, more asymmetric. Their systems in flux, still figuring out their final configurations. The old ones are faint, sparse, symmetric. They're systems that have finished evolving, where the planets have found stable orbits where collisions are rare. Our solar system is somewhere in between. Old enough that the major collisions are over, young enough that minor collisions still happen. In another few billion years, even the minor collisions will stop. The asteroid belt will be depleted, the Kuiper belt will be cleared, the debris disk will fade to almost nothing. And from a distance, the solar system will look quiet, clean. No sign of the chaos that once was. Let's talk about AU Microscopii. It's a red dwarf about 32 light-years away, only about 20 million years old. It has a bright debris disk, and in 2020, astronomers detected a planet AU Mike B, about the size of Neptune orbiting close to the star. But here's the strange part. The disk has features, moving features, bright arcs that seem to travel outward away from the star at high speeds. At first, scientists didn't know what they were seeing. Were these waves in the disk shadows cast by warps? Something else. Current research suggests they're caused by stellar flares. AU Mike is an active star prone to violent eruptions. When a flare occurs, it releases a burst of radiation and particles. That burst interacts with the dust in the disk, pushing it outward, creating a wave that propagates through the disk like a ripple on water. AU Mike is a young chaotic system. The planet is still migrating. The disk is still being sculpted. Stellar activity is interfering with the process. It's a glimpse of what our solar system might have looked like billions of years ago. Turbulent, unpredictable, still finding its shape. Here's something we often forget. Debris disks don't last forever. The dust is constantly being lost. Radiation pressure blows it away. Collisions grind it down into smaller and smaller pieces until it's too small to detect. Without something replenishing the dust, without new collisions, a debris disk will fade within a few million years. So, when we see a debris disk, we know collisions are still happening, recently, frequently enough to keep the disk supplied, and that tells us something about the age and stability of the system. A bright debris disk around an old star suggests recent instability. A planet's orbit changed, something got perturbed, collisions resumed. A faint debris disk around a young star suggests the system cleared quickly. Planets formed fast, settled into stable orbits, and collisions stopped. Every disk is a history book. You just have to know how to read it. Think about this as you drift. 4.5 billion years ago, Earth didn't exist. There was dust gas planetesimals. Slowly, over millions of years, those pieces came together, collided, stuck, grew. And at some point, a Mars-sized object hit the forming Earth. The debris from that collision became the moon. If you'd been watching from afar through something like 3IATLAS, you would have seen the impact. You would have seen the infrared spike. You would have seen the debris disk form around Earth. And you would have thought something ended there. A world was destroyed. But you would have been wrong. Something ended, yes, but something else began. The moon formed, Earth cooled, the debris cleared, and eventually life emerged. Collisions aren't just endings, they're also beginnings. The dust between worlds isn't just death, it's also potential. Somewhere out there orbiting a star we've mapped with 3IATLAS, there's a debris disk, glowing faintly, asymmetric, bright. Maybe it's the aftermath of a recent collision. Maybe two rocky planets smashed together, and now all that's left is dust and memory. Or maybe it's something else. Maybe a planet survived. Maybe it's still there wounded but intact, orbiting through the debris of its lost sibling. Maybe billions of years from now, the dust will settle, the collisions will stop, and the survivor will be alone orbiting a quiet star, carrying the scars of a violence it barely remembers. We see the dust, but we don't always see what's hiding in it. And that's the beauty and the mystery of debris disks. They're not endings, they're pauses, moments between chapters, the universe catching its breath before the next act begins. But there's another way to read the story of a solar system, not by looking at its present state, but by understanding its age. How long has it been forming? How long will it last? From birth to death, every system follows a timeline, and 3IATLAS shows us that timeline playing out in real time across the galaxy. Everything has a lifespan. Stars, planets, galaxies, even the universe itself, scientists suggest, will one day end expanding forever into cold darkness, or collapsing back into a singularity, or fading into something we can't yet imagine. But tonight, let's think smaller. Let's think about a single solar system, a star, its planets, the disk from which they formed, the debris they leave behind. How long does it all last? From birth to death, how much time does a solar system have? The answer is both comforting and unsettling. Billions of years, but not forever. Nothing lasts forever. And 3IATLAS shows us every stage. The infants, the adolescents, the middle-aged, the dying, a gallery of time frozen in light. Let's start at the beginning. Not the Big Bang, not the formation of galaxies, just the birth of a single star. It starts with a cloud, a molecular cloud vast and cold drifting through space, mostly hydrogen, some helium. Traces of heavier elements, carbon, oxygen, iron forged in previous generations of stars and scattered when they died. The cloud is thin, so thin that if you were standing inside it, you wouldn't notice. It would feel like a vacuum, but over time, small regions of the cloud become denser. Gravity pulls material together, slowly, patiently. And then, at some point, a trigger. Maybe a nearby supernova sends a shockwave through the cloud, compressing it. Maybe the passage of a spiral arm in the galaxy disturbs it. Maybe it's just random fluctuation, a spontaneous collapse. Whatever the cause, once a region becomes dense enough, gravity takes over. The collapse accelerates. Material falls inward, heating up from the compression. At the center, temperatures rise, pressures mount. And after about 10 million years, a blink in cosmic terms, the core becomes hot enough for nuclear fusion to ignite. Hydrogen atoms fuse into helium. Energy is released. Light radiates outward. A star is born. But the star isn't alone. Around it, the leftover material from the collapse forms a disk. a protoplanetary disk. We talked about these earlier. Dust and gas swirling, colliding, beginning the slow process of building planets. This stage from the birth of the star to the formation of the first planets takes about 1 to 10 million years, depending on the star's mass and the disk's density. For our sun, it took about 10 million years. The disk formed, dust grains stuck together, pebbles became boulders, boulders became planetesimals, and eventually those planetesimals collided and merged into the cores of planets. By the time the sun was 10 million years old, the planets were taking shape. Not finished, not stable, but recognizable. Rocky worlds in the inner system. Gas giants forming in the outer system. Collisions happening constantly. 3IATLAS shows us systems at this stage. Stars less than 10 million years old, still surrounded by thick, bright disks. Planets forming in real time, carving gaps, creating spirals, leaving their fingerprints in the dust. These are the infants, and they're everywhere. By about 100 million years, most of the gas in the disk is gone, blown away by stellar winds, lost to space. What remains are solid bodies, planets, asteroids, comets, and a thin veil of dust from their collisions. This is the transition from a protoplanetary disk to a debris disk. The construction phase is over. The cleanup phase begins. Our solar system was, at this stage, about 4.4 billion years ago, roughly 100 million years after the sun formed. The planets were mostly in place. Jupiter and Saturn had finished migrating. The terrestrial planets, Mercury, Venus, Earth, Mars, were still being bombarded, still accreting material, but their masses were mostly set. It was violent, chaotic. Earth was hit by Theia, forming the moon. Mars was battered by impacts that scarred its surface. The late heavy bombardment around 4.1 to 3.8 billion years ago sent waves of asteroids and comets crashing into the inner planets. But it wasn't destruction. It was refinement. Water was delivered. Volatile elements were mixed. The planets were being shaped into their final forms. 3IATLAS finds systems at this stage too. Young stars 10 to 100 million years old with faint debris disks. The gas is gone, but collisions are still frequent. Dust is still being replenished. These are the adolescents, turbulent, growing, not yet settled. Then comes stability. By about 500 million years, most solar systems have reached a kind of equilibrium. The planets are in stable orbits. The major collisions are over. The debris disks fade as the supply of colliding bodies dwindles. Our solar system entered this phase about 4 billion years ago, and it's been relatively stable ever since. Sure, there are still impacts. Asteroids still hit planets occasionally. Comets still fall toward the sun, but the frequency has dropped dramatically. The chaos has settled into routine. This is the long, quiet middle age of a solar system. The planets orbit, the star burns steadily. Billions of years pass. Life, if it emerges, has time to evolve, to diversify, to develop intelligence. Earth has been in this phase for 4 billion years, and it will stay in this phase for about another billion years, maybe more. That's a long time. Long enough for civilizations to rise and fall. Long enough for entire evolutionary trees to branch and prune. Long enough for us to look up wonder and start building telescopes. But it's not forever. Here's where it gets bittersweet. Stars don't burn forever. They run out of fuel. And when they do, they change. The sun is about 4.6 billion years old. It's a main sequence star fusing hydrogen into helium in its core. And it will continue doing that for another 5 billion years or so. But hydrogen is finite. Eventually, the core will run out. And when it does, the sun will start fusing helium into heavier elements. The core will contract. The outer layers will expand. The sun will become a red giant. It will swell enormously. Its outer layers will reach past the orbit of Mercury, maybe past Venus, possibly even past Earth. If Earth is still in its current orbit, and it might not be, Because as the sun loses mass, its gravitational pull weakens, and Earth's orbit will drift outward. It will be scorched. The oceans will evaporate. The atmosphere will be stripped away. The surface will melt. Earth, if it survives at all, will be a lifeless cinder. But here's the strange part. While the inner planets are being incinerated, the outer solar system will warm up. The habitable zone will shift outward. Mars, frozen and dead for billions of years, might briefly thaw. Its ice caps might melt. Liquid water might flow on its surface again. And farther out, some of Jupiter's and Saturn's moons, Europa and Enceladus Titan, might enter the habitable zone. Their icy shells might melt. Their subsurface oceans might be exposed. For a few million years, maybe a few tens of millions, these moons might be habitable. Life, if it exists in their oceans, might have a chance to see sunlight for the first time. It's a brief window, a last gasp, but it's something. 3. Atlas doesn't show us red giants directly. They're too evolved, too rare in the infrared surveys. But it shows us the young stars, the main sequence stars, the systems that are heading toward this fate. Every system we study is on the same timeline: birth, growth, stability, decline, death. The only difference is where they are in that timeline. After the red giant phase, the sun will shed its outer layers. They'll drift away, forming a planetary nebula, a glowing shell of gas expanding into space. What's left behind is the core, small, dense, no longer fusing. A white dwarf, about the size of Earth, but with a mass comparable to the sun. Incredibly hot at first, but cooling over billions of years. The planets, if any, survived will still orbit, but the sun will no longer provide warmth. It will be a fading ember. Eventually, it will cool, completely becoming a black dwarf, a cold, dark remnant, invisible except for its gravitational pull. The solar system will be dead, frozen, silent. And that's how it ends. Not with a bang, with a fade. But not all stars die the same way. The sun is a medium-sized star, so it becomes a white dwarf. But larger stars, those more than 8 times the sun's mass, die differently. They exhaust their hydrogen, then their helium, then carbon, oxygen, neon, silicon. Each stage burns faster than the last. Hydrogen fusion lasts billions of years. Silicon fusion lasts days. And then when the core is made of iron, fusion stops. Iron doesn't release energy when it fuses. It absorbs energy. The core can't support itself anymore, and it collapses. In less than a second, the core implodes, then rebounds. The outer layers are blasted away in a supernova, a burst of light so bright it can outshine an entire galaxy. If a planet is orbiting a star like that, it doesn't gradually die. It's obliterated, vaporized, scattered as atoms across light years. But here's the beautiful part. Those atoms don't disappear. They drift through space. They join molecular clouds. And eventually they become part of the next generation of stars and planets. The iron in your blood, the calcium in your bones, the oxygen you breathe. All of it was forged in the core of a dying star and scattered in a supernova billions of years ago. You're made of dead stars. We all are. 3IATLAS helps us see the variety. Stars of different masses at different stages of their lives. Some will end as white dwarfs. Some will explode as supernovas. Some, the most massive, will collapse into black holes. And their planets, if they have them, will follow different fates. Some will be consumed. Some will be ejected. Some will orbit the remnant silent and cold for billions of years. There's no single story. Every system is unique. Every timeline is different. But the pattern is the same: birth, growth, stability, decline, death. It's the cycle of everything. Here's something we often forget. The universe is 13.8 billion years old. The sun is 4.6 billion years old. That means the sun formed about 9 billion years after the Big Bang. But stars were forming long before the sun. The first stars formed only a few 100 million years after the Big Bang. Some of those stars have already died. Some have become white dwarfs. Some have exploded. And their planets, if they had planets, are long gone. Destroyed, scattered, recycled. We're not living in the early universe. We're living in a mature universe. A universe that's already seen countless cycles of birth and death. And the stars we see in the night sky, most of them are younger than the sun. The Milky Way is still forming stars, still creating new systems. So 3IATLAS isn't just showing us the past, it's showing us the future. Systems that are younger than ours are previews of what we once were. Systems that are older are previews of what we'll become. Let me ask you this. If you could witness one moment in the life of a solar system, which would you choose? The birth, when the star ignites and the disk begins to swirl. The formation of the first planet pulling itself together from dust. The moment life emerges, if it does. Or the end, when the star swells and the planets fall silent. Each moment is profound. Each tells part of the story. And we're lucky. We're living in the middle, in the stable phase. When the chaos has settled and the end is still distant. When life has had time to evolve and there's still time ahead. Not forever, but enough. Our solar system is middle-aged. The sun is halfway through its main sequence lifetime. Earth has another billion years, maybe a bit more, before the sun gets too bright and the oceans start to evaporate. A billion years. It sounds like a lot. And it is. It's longer than complex life has existed on Earth. It's longer than humans by far. But it's not infinite. It's a deadline. A clock ticking in the background. What will we do with that time? Will we stay on Earth watching the clock run down? Or will we leave spreading to other planets, other stars carrying life with us? We don't know. We're still figuring it out. But the clock is ticking, and 3IATLAS is a reminder. Every system has its time, and time eventually runs out. Here's the comforting part. Even when a solar system dies, the story doesn't end. The atoms scatter. They join new clouds. They form new stars, new planets, new chances. The universe recycles. Nothing is truly lost. It's just transformed. The carbon in the trees, the nitrogen in the air, the water in the oceans. All of it has been through this cycle before. Multiple times, formed in one star, scattered in its death, gathered into another star, scattered again, gathered again. You're not just made of stars. You're made of many stars, generations of them. And one day, billions of years from now, the atoms that make up your body will be scattered too. They'll drift through space. They'll join a cloud. They'll become part of a new star, a new planet, maybe even new life. You're not permanent, but you're part of something that is. 3IATLAS shows us the timeline, the beginning, the middle, the end. And by seeing all of it at once, systems at every stage spread across the galaxy, we understand our place. We're not at the beginning, we're not at the end. We're in between, in the long, stable, precious middle. And we have time, not forever, but enough. Enough to look up, to wonder, to ask questions, to build telescopes, to map the sky, to find other systems, other worlds, other possibilities. Enough to appreciate the moment, this moment, the one where we're here looking out into the vastness and realizing we're part of it. So rest in that. The knowledge that you're temporary but connected, finite but part of something infinite. The stars will keep burning, for now. The planets will keep orbiting, for now. And we'll keep looking, mapping, wondering, for now. And now is enough. So, we've traced the arc of time from the first spark of stellar birth to the final cooling embers. But what does all of this mean? What have we learned from these distant systems, these infrared glimpses into alien worlds? Let's gather the pieces, now, all the clues 3IATLAS has given us, and see what they reveal about our place in this vast, quiet universe. We've walked a long way tonight, through invisible light and hidden disks, through forming planets and migrating giants, through collisions and debris, through time itself, from birth to death and back again. And now, as we near the end, Let me ask you something. Are we any closer to answering the question we started with? Are we alone? The truth is 3IATLAS doesn't answer that question. Not directly. It doesn't show us alien cities or radio signals. It doesn't detect life. But it does something just as profound. It shows us the conditions, the ingredients, the stages, the possibilities. It shows us that water is common, that carbon is everywhere, that protoplanetary disks form around almost every star, that planets are the rule, not the exception. It shows us that the universe is not hostile to life. It's full of the pieces. Whether those pieces come together, whether chemistry becomes biology, whether biology becomes intelligence, that's still unknown. But the raw materials are there, scattered across the galaxy, waiting in the disks, locked in the ice, floating in the atmospheres of worlds we'll never visit. The universe is ready. The question is whether life knows how to begin. Here's what we've learned. Every solar system is different. Every disk is unique. Every planet follows its own path. Some systems have hot Jupiters. Some have super Earths. Some have nothing but debris. Some are calm. Some are chaotic. Some are young. Some are old. There's no template, no standard model, no correct way for a solar system to form. Our solar system with its rocky planets, close-in gas giants farther out. A stable star, a large moon stabilizing Earth's tilt, is just one outcome, one roll of the dice. And that means we can't assume life requires a solar system like ours. Maybe it does. Maybe Earth-like conditions are essential. Maybe we're rare, precious, unlikely. Or maybe life is more flexible than we think. Maybe it can adapt to mini Neptunes, to tidally locked worlds, to moons orbiting gas giants. Maybe the habitable zone is wider than we thought. Maybe habitable means something we haven't imagined yet. We don't know. And 3IATLAS reminds us we don't know, because the universe is bigger, stranger, more diverse than our models predicted. Let's think about what we're really doing when we study these systems. We're not just collecting data, we're telling stories. Every infrared glow is a story. Every gap in a disk is a chapter. Every debris field is an epilogue. Some stories are violent. Planets collide. Giants migrate. Inner systems are destroyed. Some stories are patient. Dust grains stick together. Planetesimals grow. Worlds take shape over millions of years. Some stories are unfinished. Systems still forming. Disks still bright. Planets still carving their paths. And some stories are ending, stars cooling, planets freezing. The long, slow fade into darkness. The 3IATLAS is a library, and we're the readers piecing together the narratives from fragments, from clues, from light that traveled years or centuries to reach us. Here's something I want you to think about. Right now, at this very moment, somewhere hundreds of light years away, a planet is forming. Dust is colliding. A core is growing. Gravity is pulling material inward grain by grain. That planet doesn't know we're watching. It doesn't know we've built telescopes, mapped its disk, analyzed its chemistry. It's just forming, slowly, patiently, following the laws of physics, the pull of gravity, the randomness of collisions. In 1,000,000 years, it might be a rocky world. In 10 million years, it might have an atmosphere. In 1,000,000,000 years, it might have oceans, life, intelligence, or maybe not. Maybe it'll be ejected by a migrating giant. Maybe it'll collide with another forming planet and shatter. Maybe the star will flare and strip its atmosphere away. We can't know. We can only watch and wonder and keep looking. Here's the mistake we make over and over. We think finding life is about searching for exact copies of Earth, same size, same distance from the star, same atmosphere, same conditions. But the universe doesn't make copies, it makes variations. 3IATLAS shows us that. Every system is a variation on the theme of planetary formation. Some variations are subtle, some are dramatic, but none are identical. So if life exists elsewhere, it probably doesn't look like Earth. It probably doesn't orbit a star like the sun. It probably doesn't have our atmosphere, our oceans, our history. It'll be something else, something shaped by different chemistry, different temperatures, different timelines. And that's okay. That's beautiful even, because it means life, if it's out there, is diverse, adaptable, creative, just like the universe that made it. Let me tell you about a moment that changed how scientists think about habitability. In 2017, NASA announced the discovery of 7 Earth-sized planets orbiting a star called TRAPPIST-1, about 40 light-years away. 3 of those planets are in the habitable zone, 3 in a single system. The excitement was immediate. Headlines proclaimed 7 Earth-like worlds found, best chance yet to find alien life. But then the details emerged. TRAPPIST-1 is a red dwarf, small, cool, prone to flares. The planets orbit very close. The outermost one is closer to TRAPPIST-1 than Mercury is to the Sun. They're probably tidally locked. One side always facing the star, the other always in darkness. Are they habitable, maybe? If they have thick atmospheres to redistribute heat. If they have magnetic fields to deflect stellar wind. If the star's flares aren't too frequent or too violent. But they're not Earth. They're not even close. They're something stranger. Something we're still trying to understand. TRAPPIST-1 reminded us habitable doesn't mean familiar. It means possible, and possibility takes many forms. 3IATLAS helps us find those forms. The systems that don't fit our expectations, the ones that challenge our assumptions, the ones that expand the boundaries of what we think life can tolerate. Here's a question for you. If we do find life, not intelligent life, not civilizations, just simple microbial life clinging to a rock or floating in an ocean, how will it change us? Will we feel less alone or more lonely? Realizing that even with life scattered across the galaxy, we might never meet, never communicate, never know each other. Will we feel humbled or emboldened, knowing that life is resilient, persistent, woven into the fabric of the universe? I think it'll be both. Comfort and loneliness, humility and pride. The realization that we're part of something vast and also that we're still in some fundamental way separate. But maybe that's okay. Maybe the search is more important than the answer. Maybe the act of looking, building telescopes, mapping disks, analyzing spectra is what defines us. We're a species that looks up, that wonders, that refuses to accept ignorance when knowledge is within reach. And 3IATLAS is part of that. A tool, a map, a guide to the invisible. Think about how far we've come. 200 years ago, we didn't know infrared light existed. 100 years ago, we didn't know other galaxies existed. 50 years ago, we didn't know if other stars had planets. Now we've mapped thousands of exoplanets. We've analyzed their atmospheres. We've watched solar systems forming in real time. In another 50 years, what will we know? In another 100, maybe we'll have found life. Maybe we'll have identified biosignatures in the atmosphere of a rocky planet orbiting a sun-like star. Maybe we'll have sent probes to nearby systems. Tiny, fast spacecraft powered by lasers traveling at a fraction of the speed of light, reaching Proxima Centauri in 20 years instead of thousands. Maybe we'll have telescopes powerful enough to image the surfaces of exoplanets, to see continents, oceans, clouds, to watch weather patterns, seasonal changes, maybe even signs of technology. Or maybe we won't. Maybe the search will continue generation after generation with no definitive answer, no signal, no proof. But even that would tell us something. It would tell us that life, if it exists, is rare, precious, worth protecting. Here's the thing about 3IATLAS. It's not the end. It's a step. One tool in a growing arsenal of techniques for studying exoplanets and their formation. There will be more surveys, more telescopes, more data. The James Webb Space Telescope is already transforming what we know about exoplanet atmospheres. Future missions like the Habitable Worlds Observatory, still in the planning stages, will take it even further. We're building a picture, piece by piece, spectrum by spectrum, system by system. And with each piece, the picture gets clearer, not simpler. Clearer, more detailed, more complex, more beautiful. So, what does 3IATLAS reveal about alien solar systems? It reveals diversity, complexity, the full spectrum of outcomes when gravity, chemistry, and time interact. It reveals that planets are common, that water is common, that the ingredients for life are everywhere. But it also reveals that conditions matter, that being in the habitable zone isn't enough, that stars vary, that migration happens, that collisions reshape systems. It reveals that every system is a story, and every story is different. Our story, Earth's story, is just one. Maybe it's rare, maybe it's common. We don't know yet, but we know it's not the only one, and that's enough. That's profound, because it means we're not alone in the sense that matters most. We're not alone in a universe full of dead rocks orbiting dead stars. We're part of a universe where planets form, where chemistry happens, where possibilities exist. Whether those possibilities become realities, whether life emerges, whether it survives, whether it looks up and wonders the same things we do. That's the question we're still asking. And 3IATLAS is helping us ask it better. As you drift now, let the thought settle gently. Somewhere in a disk of dust orbiting a distant star, a planet is forming. Slowly, patiently, grain by grain. It doesn't know it's being watched. It doesn't know we exist. It's just forming, following the same physics that formed Earth billions of years ago. Maybe it'll survive. Maybe it'll thrive. Maybe billions of years from now, something will live there. Something that looks up at its own night sky, sees the faint glow of our sun and wonders. Or maybe it won't. Maybe it'll be destroyed in a collision. Maybe the star will flare and strip its atmosphere. Maybe it'll migrate into the fire and be consumed. We can't know. Not yet. But we can look, we can map, we can learn. And that's what we're doing. Not just with 3IATLAS, but with every telescope, every mission, every question we ask. We're looking quietly, patiently, waiting for the universe to reveal its secrets. And it is, slowly, one photon at a time. Here's the last thing I want to leave you with. The universe is old, 13.8 billion years. And in all that time, in all that vastness with all those stars and all those planets, it's possible, maybe even likely, that we're not the first to look up and wonder. Maybe others have asked the same questions, built their own telescopes, mapped their own skies, searched for us the way we're searching for them. Maybe they found us. Maybe they saw the faint infrared glow of our sun, the spectral signature of Earth's atmosphere, and thought there's something there, something worth investigating. Or maybe they didn't. Maybe we're separated by too much space, too much time. Maybe their signals haven't reached us yet. Maybe ours haven't reached them. Or maybe we're alone. Maybe we're the first, the only ones to look up to wonder, to build something like 3IATLAS and peer into the darkness, hoping for an answer. Either way, the search matters, because even if we never find life, we'll have found something just as important: the limits of our loneliness, the edges of the possible, the boundaries of the universe's hospitality. And that's worth knowing. So, tonight we've drifted through the silence between stars. We've seen the hidden light, the invisible architecture, the chemistry of elsewhere. We've watched planets form and migrate and collide. We've traced the timeline from birth to death. And what have we learned? That the universe is not empty, not silent, not hostile. It's full, busy, patient. It's building worlds one collision at a time. It's mixing chemistry one molecule at a time. It's writing stories one system at a time. And we're here, watching, learning, part of the story, not separate from it. We're made of stars. We orbit a star. We look at other stars and see ourselves reflected not as we are, but as we were, as we will be, as we could have been. 3IATLAS doesn't answer the question, are we alone? but it gives us the tools to keep asking, the maps, the clues, the directions, and maybe that's enough for now, for tonight. You've been here with me through all of this, through infrared and dust, through time and silence, through the long, quiet story of how worlds are made. Thank you for listening, for staying, for letting these thoughts drift through your mind as you drift towards sleep. There are more stories, more systems, more mysteries waiting in the dark, and we'll keep looking, keep mapping, keep wondering. The search continues, quietly, patiently, and so do we. Sleep well, dream gently. And when you wake, look up. The stars are still there, still burning, still holding their secrets. And we're still here, still asking, still hoping. Good night.